minute or two because I didn't give you a 2-minute warning. So this is your 2-minute warning, and we will get started in 2 minutes. Good. Okay. Phyllis, would you like to reconvene the meeting?
Since we did not gavel out, I will not gavel in. Good morning, welcome back. Glad to see everyone. We have got a busy day, but we're going to learn a lot, and it's going to be, thank you.
Okay. So as Phyllis noted, you have a busy day today. Like we talked about yesterday, today is entirely focused on liquid waste and the projects and programs that come up underneath that. We established a lot of new vocabulary words yesterday. We're going to continue to use those words throughout today, so just keep those in mind and keep them handy. One thing I do have to note, there are 9 of you, and I need 10 for a quorum. So we are waiting for 2 more. We expect 2 more. You should be 11 before you have to vote. But if nothing changes, if those 2 for some reason are not able to make it, keep in mind, we will not be voting this afternoon, okay? We can't do that without a quorum. We won't. But the 9 of you who are here are the cool kids, and y'all get to ask a lot of questions today. Are y'all ready to get started? Any questions, comments, concerns about the agenda going forward for the day? I want to make sure we address anything we need to. Seeing none. Doug and Brittany, are y'all ready? Come on down.
Is this thing on? Perfect. Good morning, everyone. How are you guys? Good. My name is Brittany Califf. I have been at the Savannah River site for almost 10 years now. My current role is in the Department of Energy as a program manager over the Defense Waste Processing Facility, better known as DWPF. That's a mouthful. And we'll be talking to you guys. We'll be giving you a brief overview of the vitrification process and the Climb to 9 initiatives that Mike and Joel had talked about earlier. Specifically, we'll be talking about the DWPF side of the house, those initiatives, what we've accomplished and what we are still working towards. And this presentation will be presented by Doug Bumgardner. He is the DWPF Accelerated Program Manager. And yeah, I will let him talk, and without further ado, we will get into the presentation. So these are just some acronyms, and we've got a video to kind of talk to you the brief overview of DWPF, and we'll let y'all play that and watch this.
Safely and permanently immobilizing radioactive liquid waste is a key mission at the U.S. Department of Energy's Savannah River site. Savannah River mission completion operates all the SRS liquid waste facilities for the Department of Energy. The mission is to treat the waste and close the high-activity radioactive waste tanks at the Savannah River site. Part of the liquid waste system supports continued chemical separations operations of H Canyon. However, the majority of the highly radioactive waste is a legacy of nuclear weapons production created during the Cold War. About 34 million gallons of this radioactive waste are now stored in numerous underground carbon steel tanks at SRS. The waste has millions of curies of radioactivity and requires permanent isolation from the environment. The radioactive waste is primarily in two forms, sludge and salt. The sludge makes up less than 8% of the waste volume, but contains nearly half of the curies, or amount of radioactivity. The remainder of the waste is in the form of salt, which is about 92% of the volume and approximately half of the radioactivity. Two key facilities safely treat and dispose of the salt and sludge wastes: the Salt Waste Processing Facility and the Defense Waste Processing Facility. The Salt Waste Processing Facility, or SWPF, is treating the salt portion of the waste. It began operating in 2021. The salt waste undergoes a two-step decontamination process at SWPF. The first step removes strontium and long-lived actinides from the salt waste through the process of absorption. The second step removes the radioactive cesium by extraction. This part of the SWPF process uses a special solvent and over 30 centrifugal contactors to mix and separate the solutions. Both the absorbed waste and the extracted cesium solution are transferred to the Defense Waste Processing Facility, or DWPF, and combined with the sludge waste for vitrification. Then the remaining salt solution that has been decontaminated is ready for treatment and final disposal at the saltstone production facility. Saltstone is produced by adding dry grout feeds to the decontaminated salt solution. This grout solution is then pumped to an engineered state-permitted unit called a saltstone disposal unit, where it hardens to form a final disposition form. The saltstone disposal units, or SDUs, are a critical part of the liquid waste system, as they are permanent disposal units that will hold solidified decontaminated salt solution at SRS. 3 megavolume SDUs have been built at SRS, and several more are under construction. The large-scale units can hold 33 million gallons, equivalent to the amount of water that would fill 55 Olympic-sized swimming pools. DWPF is treating the sludge portion of the waste. It began operating in 1996. DWPF converts the highly radioactive portion of the liquid waste, the sludge, into a solid glass form suitable for safe, long-term storage. Scientists have long considered this glassification process, called vitrification, as the preferred option for treating long-lived radioactive waste. To turn waste into glass, a sand-like borosilicate glass called frit is mixed with the waste and sent to the plant's 75-ton steel and ceramic melter. In the melter, the waste frit mixture is heated to nearly 2100 degrees Fahrenheit until molten. This molten glass waste mixture is then poured in a pencil-thin stream into stainless steel canisters to cool and harden. Each canister is 10 feet tall and 2 feet in diameter. Typically, it takes a little over a day to fill one canister. A filled DWPF canister weighs about 5,000 pounds. After a canister is filled, the exterior is blasted with a frit water mixture to remove contamination. A stainless steel plug is fitted into the neck of each filled canister, and the canister is welded shut using a current of 250,000 amps applied for 1.5 seconds. While 80,000 pounds of force simultaneously rams the plug into the neck of the canister. The resulting weld is as strong as the 3/8-inch thick stainless steel canister itself. More than 4,300 canisters have been filled at DWPF since it began operating. A specially designed shielded canister transporter moves each sealed canister one at a time from DWPF to interim storage buildings adjacent to the facility. At the storage buildings, canisters are lowered by the transporter into seismically qualified underground reinforced concrete vaults. The storage buildings are being modified to double the capacity by stacking 2 canisters in each storage position, exceeding the total number of canisters projected to be produced by DWPF. Double stacking canisters instead of building another storage facility saves at least $100 million in taxpayers' money. The canisters will be safely stored at SRS until a federal repository is established. Once the salt and sludge are removed from the waste tanks, final tank cleaning and operational closure can begin. The tanks are first cleaned to ensure they meet the long-term closure objectives. Next, the tanks are isolated from the liquid waste system by deactivating transfer paths and disconnecting normal services. A specifically formulated grout is then poured into the cleaned underground tanks. The grout binds residual radioactivity and finalizes the closure process. It's the goal of Savannah River mission completion to safely remove the waste and close the remaining waste tanks by the year 2037. Until then, all the liquid waste facilities will continue to work together as an integrated and interconnected system. By executing the mission, the liquid waste team at the Savannah River site reduces radiological risks to employees, surrounding communities, and the environment, ensuring a safer future for everyone.
You good? All right, good morning. I'm Doug Baumgardner. As Brittany mentioned, I'm managing projects at DWPF that are intended to allow DWPF to process waste faster. We've got some facts here, so I don't lie to you guys. The mission at DWPF is really to take almost all of the radioactive material, almost all of the curies, and encapsulate that into glass. So it ends up being not as much volume as is processed through the other facilities, but as SWPF processes the radioactive component of that, most all of that gets sent to DWPF. And then the sludge side of things from the tank farm, all of the sludge waste gets sent to DWPF. So at the end of the day, the facilities all work together, ultimately with almost all of the radioactive material being encapsulated in glass at DWPF. So we'll go through a little bit more information on the process at DWPF itself, and then we'll cover some specific improvement activities that we've been working through. So as I mentioned, everything starts in the tank farms. Those tanks are really what we're after, emptying and closing those tanks. There's 2 streams there, the sludge stream, which is sort of the peanut butter consistency that we've talked about, and then the salt stream that can either be a salt cake or a thick liquid. The important thing to know about that is getting that material out of the tank, all of those activities create additional liquid that ultimately get processed through the facilities, eventually getting sent through all the way through ETF and some parts into saltstone. Once a sludge batch is made in the tank farm, which involves both waste removal and some pre-treatment activities, it's then qualified. There's a number of requirements for making glass, both from a sort of a regulatory standpoint as well as a processing standpoint. So when we put together a sludge batch in the tank farm, samples of that batch are taken. SRNL evaluates that batch, including at a small scale, making glass out of that to demonstrate the process. And typically, a sludge batch that we put together can be processed in a couple-year period of time. So we go through salt batches much more quickly than that, but typically the sludge batches are at DWPF for a little while, but all of that is demonstrated in the lab before we start processing in the plant. The first step, once we receive waste at DWPF, is the SRAT, the Sludge Receipt and Adjustment Tank. In that tank, and I'll go through this in a little bit more detail on the next slide, we receive the waste, and then we add acids to the waste, and we do some boiling to reduce volume. At that point, the basic chemistry of the batch is set, and the material is then transferred to the SME, the slurry mix evaporator. That is where we add the glass former, the frit. So frit is a sort of a sand-like material that's specifically made for us, depending on the chemistry of our waste, that's used to actually form the glass. So in the SME, SRAT, we've received and treated the waste to get to the right chemistry. In the SME, we add the glass former. Once that's done, then we're ready to transfer to the melter feed tank, which is just a mixing vessel that keeps things in suspension as we feed the melter. And in the melter, we heat the waste till it's like lava, and then pour it into the cans. The cans are sealed, decontaminated, and transported for interim storage. Most of the steps in that process generate a little bit of water. As we evaporate water out of the waste when it comes in, that water is collected, and it's called DWPF Recycle. DWPF Recycle is then sent back to the tank farm, where it can be used to dissolve more salt. It could be evaporated. Different ways that we'll use recycle once it gets back to the tank farm. Each of the SRAT and SME vessels are essentially the same design. There's an agitator, heating and cooling coils, and then pumps to transfer the material. So again, in the SRAT, we receive sludge waste from the tank farm. The next step, we receive MST sludge slurry from SWPF. That's the actinide portion of their stream. Once that's received, typically we have to concentrate that, boil it to remove some of the water, have less volume so that we can then move on to the next step. And in the next steps, we add nitric acid, which really changes the chemical properties so that chemistry is better able to hold the radioactive material, and glycolic acid, which changes the physical properties so that the material is easier to pump through the system. So it changes takes it from peanut butter to something a little bit thinner than that could actually be processed at higher solids concentrations. Once that's done, each of those steps typically involves some amount of sampling and analysis to demonstrate that we're on track for where we want to be in terms of what the chemistry looks like. Once that's completed, that material is transferred to the SME. In the SME, like I said, we add frit, which is a ground glass component that we use to make glass in the melter. That's done in two different ways. One, as we decontaminate the canisters, that is done using frit, air, and water. So the frit that's used for decontaminating canisters is transferred into the SME as that's done. And then once we've decontaminated the number of canisters, sort of typically a SRAT or SME batch is about 5 canisters worth of waste in each batch. So as we decontaminate the canisters that are available, there typically is additional frit that needs to be added, which we call process frit or bulk frit, and that's done as a separate slurry transfer. And again, as those things are done, each of those steps is adding a little bit of liquid into the system, That's really not what you want to try to melt. So the SME also evaporates liquid to remove liquid from the system before we transfer to the melter. So each of these vessels is about a 12-foot diameter vessel. They're about 18 feet tall, and they normally hold about 9,000 gallons. That's kind of the normal working volume. In order for us to complete the mission in 2037, which is our goal, we have to make about 300 canisters per year on average. In order to do that, accounting for planned downtime in the system, we have to be able to make a SRS batch in a period of about 5 days. So that's kind of what our target is when we talk about improvements. That's where we're trying to get to. Similar thing for the SME. Okay. Once the SME is actually where we ultimately confirm that the batch meets all the requirements to make good glass, that both will work for our melter as well as will meet any requirements for storage. From the SME, the material's transferred to the melter feed tank. That's really the same type of vessel as the SRS and SME. It has coils, agitator pumps. It's the same size. The only thing that's going on there is the material's being mixed to keep everything suspended, and then fed to the melter. The melter feed is a loop where we pump about 100 gallons a minute in recirculation, and then typically about a gallon a minute of feed gets sent to the melter, is added to the melt pool, and then when you may have heard in the video where they talked about a pencil thin stream coming out of the melter into the can, that stream coming into the can matches up with the feed rate. So you get a kind of a stable level in the melter, everything's heated to where it needs to be. You draw a vacuum on the pour spout, which enables the melted waste frit mixture to be pulled up and then falls into the canister. Typically, on the video, it said it takes a little bit more than a day to make a canister. Normally, where we're processing right now, we're processing about 20 hours per canister. And that rate is fast enough to support the 300 cans a year type number and the processing needed to meet closures in 2037. I think they may have said this in the video. I'm kind of repeating information. I can remember when I came to Savannah Riverside, I had no idea what was going on. So everything was a learning experience. So if I'm repeating things, hopefully that is not a bad thing. So the canisters are about a 2-foot diameter. They're 10 feet tall. They normally get filled to 100 inches. The empty weight of the canister is about 1,300 pounds, and the full weight is about 5,600 pounds. The melter itself is almost 11-foot high and about a little bit more than 8-foot diameter. The thickness of the melter is about 1.5 inches thick. It weighs about 65 tons. We've used 3 melters at DWPF so far. We're on our 3rd. That was installed in 2017. The melting is done by adding, there's electrodes. You're passing current through the waste to heat it, and that's about 2,200 kilowatts of power. Okay. Once the cans are filled, there's an there's an inner closure plug that's put in while the can is hot. As it cools, that then forms a tight seal. That seal is checked before you go to the next step. Once that inner seal is installed, the can has to cool before it gets decontaminated. So normally canister gets below 100 degrees C before you do the decontamination, so that when you spray it with water, you don't immediately start to boil the water. So inner canister closure plug's installed, the canister is cooled, confirm that you got a good seal on the inner closure plug, and then the canister is moved using a bunch of remote equipment. There's a number of cranes, trains, trolleys inside of DWPF that move canisters from one area to the next. The can is then inserted in a vessel that's sort of like a touchless car wash kind of thing. The canister is hung on a grapple. There's spray nozzles that operate in a sequence so that you're ensuring that each part of the canister has been blasted with the frit water mixture to remove any surface contamination. As that's done, the canister is also moving, again, just to make sure that as it goes through that process, every bit of the canister's been cleaned. Once canister's decontaminated or cleaned, it's moved to a station where we then take a small swipe and check several positions on the canister to confirm that it's clean or decontaminated. That's all done remotely. Once you've confirmed it's clean, then you go to the next step, which is welding the final closure plug, which you can see, and they showed in the video, there's the taper plug is inserted in the top, and then in about a 2-second period, you apply about 100,000 pounds of force, 80 to 100,000 pounds of force with the ram, while you're also putting electric current through that then heats and fuses the area between the neck of the can and the plug. Once all that's done, the shielded canister transporter is used to move the canister from the canyon building. Again, there's a series of trolleys and cranes inside the canister to move the can to a position where the shielded canister transporter can pick up the can, draw the can into the sort of the center of the shielded canister transporter, where there's shielding to protect workers from the radiation. And then that transporter travels about 100 yards from the canyon building to the glass waste storage building, where the canisters are then lowered into the storage positions. We've currently poured a little bit more than 4,400 of the about 8,100 canisters that we need to make to complete the mission. We've just recently completed modifications to allow double stacking in glass waste storage building 1. That's the 2 cans on top of each other. And we're currently modifying glass waste storage building 2 so that that can also be double stacked. As part of that process, there are some temperature limits for storing the canisters with the concrete. Part of how the canisters are positioned in the glass waste storage building and the natural ventilation of the glass waste storage buildings, as well as limits on the canister Curie content or heat loading, ensure that none of the canisters get over temperature while being stored. So with these 2 buildings, we'll have enough storage positions to store all the canisters that we need to make for the mission. All right, so DWPF's been operating since since 1996. The original planning for DWPF or for vitrifying waste goes way back in time. The design started in the late 70s. Some of the project planning, a lot of the construction activities were completed in the 80s, and then cold testing started in 1993, which is about when I showed up on site, not to do the cold testing, but just random fact. And so I've seen DWPF run since the beginning. The original design basis for DWPF was to process at a rate of 400 cans a year. Like I said before, we need to process about 300 cans a year in order to finish the mission in 2037. Looking backwards in time from the 90s through about 2010, there was a couple things that limited DWPF production, one of which was, at that time, the melter itself was the slowest part of the process. And in 2010, we installed bubblers to mix the waste in the melter so that the melter could process faster. So that was one of our first things that took away a constraint to enable DWPF to process faster. Also during that time, the tank farm was limited on tank space. So both the act of performing waste removal and preparing sludge batches, as well as processing with DWPF, created liquid. In that time, there was no salt processing going on, so it was difficult to manage how fast you could process sludge with the limited space. And then in 2010, we started doing salt processing on our pilot scale plants, and that started to open up some salt space, which both demonstrated what we're going to do at SWPF, as well as let us keep going in terms of removing sludge waste. So the majority of our improvements for DWPF that we're currently working have been completed. I'll start out with one of the first changes that we implemented when SRMC came into play was introduction of the glycolic acid flow sheet. Previous flow sheet used formic acid. Formic acid has some personnel hazards, as well as when the formic acid was added into the SRAT, it created hydrogen, which is a flammability concern. And so there was controls in place to make sure that the hydrogen gases, any flammable gases that we're creating, were purged. So you added a stream to make sure that, an air stream basically, to make sure that any flammable gases were removed. That additional air purge stream then affects how the vessel pressures and ability to really operate the vessels at their full capacity. So introduction of glycolic acid got us to a safer point because it removed a part of the hydrogen hazard or flammability hazard. And then it also enables us to process faster. We can process at higher steam rates. The waste properties themselves are a little bit better with the glycolic as well. So that was one of the first changes that we've made that put us on the path to supporting SWPF processing 9 million gallons a year and DWPF processing 3 million gallons a year. And then there's a couple of changes that are sort of associated with that on the climb to 9. There's a reduced purge, implement glycolic controls. Both of those things are just, as that flow sheet was implemented, we could change some of the limits where we were processing. Once we opened that up, that then enabled us to really start making changes that could allow us to process faster. So when we implemented the bubblers in the 2010 timeframe, the critical path, the slowest part of the process ends up being the SRAT process. So things that we do in the SRAT are basically add the waste, add the acids, and then boil. So once we got to the point where we could reduce the purge controls, then that opened up the ability to add acids faster. It enabled us to steam the vessels faster so we could evaporate faster. And ultimately, it ended up enabling us to add both the strip effluent stream from SWPF and the MST sludge solid stream from SWPF at a faster rate. So all those things are basically out of one process change that then enabled us to implement a series of other changes that has helped the SRAT go faster. I think Mike mentioned yesterday that the cycle time for the SRAT's been reduced by about 25%. We have demonstrated that we can process a SRAT through the plant in 5 days or less. There's a number of other changes on here that are sort of vague. Optimize batch management, batch material tracking, idle time improvements. So there's a number of things in the process where all the facilities have to interface together. Power is one. I think Mike showed the gear chart yesterday. Everything's got to be synced up, working together. So there's a number of changes we made to get to that 25% improvement that were just paying attention to exactly how quickly we're doing things. So not really changing the process itself, but being more aware that we're about to finish the steaming, so we need to be ready for the next step. So there's a number of things that really didn't change the process, but we've just been focused on keeping track of what we're doing, what are the steps in the process that are taking the longest time, and making sure we're doing those as efficiently as possible. The remaining activities, on the climb to 9 are concurrent transfers at the low point. So the low point pump bed at DWPF, there's a cell there that the salt feed stream that goes to SWPF and the recycle stream that goes to the tank farm go through the same cell. We had some requirements in place that you could only do one of those at a time. We just implemented this past weekend a different set of controls so that you could do those things at the same time. Keep hitting the wrong button. The one place in DWPF where there's two parallel paths, you could do two things at one time, or a failure wouldn't immediately shut you down, is the canister decontamination. There's 2 vessels to do canister decontamination. One of those is out of service. So one of our improvements is to get that system back in service. That way we'll be more efficient at how quickly we can decontaminate canisters and keep the line moving. The rest of the changes for our climb to 9 will be implemented next spring. We have I think Mike talked yesterday about, we have a system where we try to take all the facilities down in a planned outage at one time. So we are planning for an outage for next April timeframe. And there's a number of our remaining improvements, the crane upgrades. I know Mike talked about lag storage which is adding more tank space for strip effluent storage, ability to transfer strip effluent not only to the SRAT, but also to the SME, where it can be boiled. Those changes will all be implemented. They require downtime, changes to the plant in order to be implemented. So those will all be implemented in that April timeframe outage. And then the other big initiative is increasing our number of critical spares. just by nature of things, the pumps, agitators that we have in the process wear out eventually. In our history, we've normally rebuilt those, and we're trying to buy new components so that we don't have to immediately rebuild something as part of the critical path in terms of our processing. So this is kind of like a donut spare tire versus a full-size spare tire. You can still, in a lot of cases, drive on the donut, but not for very far or very fast. So it's the same kind of thing. We want to get the full-size spare tire so that when we have an equipment fail, we can put the new equipment in, keep going, and then offline fix the broken equipment. All right, so again, as we went through our optimizations, the very first thing we focused on was safety, implementing the flow sheet change from formic acid to glycolic acid, which not only is better for the personnel, has less hazards for the personnel, but also creates less hydrogen, creates less of a flammability concern in the processing vessels. Our next main, we've demonstrated through our other changes, again, I'll go out of order a little bit, but when we look at our continuous improvement, we've demonstrated that we can process the SRS, the SME, and the melter at high enough rates instantaneously to be able to support our production demands and completing the mission in 2037. The things we're focused on now are really making the plant more reliable, replacing old, obsolete components, buying spare components so that when we do have failures, we can respond to that more quickly, and that way we can keep the car driving. So instead of getting stuck in traffic, we want to just be on the highway, just cruising along. And that's our real focus as we continue, is making the plant more reliable. All of those things then support DWPF doing its part in the mission to support closure of the waste tanks. So out of all that, you should remember that DWPF is the place where we take nearly all of the radioactive material, immobilize it by encapsulating it, vitrifying it. We've completed process modifications where we've demonstrated we can meet the rates required to support 9 million gallons a year at SWPF. Our remaining improvements will make us more reliable and provide more flexibility in terms of how the plants interface. Those improvements will be made in next spring's outage. And then with all of that, DWPF has the capability to support the mission need in completing the mission in 2037. And that's it.
All right, folks, looking around the table. Phyllis, your card's already up. You're starting early this morning.
Just part of the reason, Phyllis Brick Cab, sorry. First thing I want to say is either I've finally hit the right learning curve in my brain, or this is truly the best explanation of this that I have ever seen in the 4.5 years. I finally understand it from beginning to end, I think. And that in itself is amazing. Thank you for that. So I have a couple of questions. One, the question of heat was mentioned yesterday, and then something you said, did you say that at some point you add heat? You have to heat it up even more than it naturally?
So there's a couple places in the process where we add heat. So in the SRS and SME, we add heat to be able to evaporate water. In the melter, of course, we're adding heat to get it hot enough to melt. Once we're past that process, there's nothing that we do that actually adds heat into the waste. In part of the process, of course, to make the canister closure weld, there's heat there for the weld itself. But really, once you get past the melter, there's nothing that's adding heat into the canister. Okay. There are places where we check before as you come out of the melter, out of the melt cell, there's a number of checks to confirm that the canister is cooling to temperatures that it should, so that when you decontaminate it, you don't make too much steam. When you do your leak checks, it's good. So there's a number of places along the way where you check the temperature before it gets to the storage.
Okay, then my second question is, once all of that is done and you're putting it in this temporary storage place, how hot is it? I mean, if you walked by it, you notice, or are you allowed to get that close? I don't know.
Yeah, so from before a canister exits the building, it'll have to be less than 70 C, which is still pretty warm, but it'll be a lot cooler than that by the time it gets to the glass waste storage building, just based on, the number of steps it goes through to get there. One of the things that's protected in the glass waste storage building itself, there's some temperature limits for concrete, and so the canisters themselves, the radioactive decay generates heat. So all of that's managed to ensure that we don't challenge the temperature limits for the concrete, which I think is like 150 degrees F. But from a personnel standpoint, you can walk on top of the canister storage area. Yeah, so this guy right here is standing on top of the vault where the canisters are stored. And it's a pretty thick pad there.
The top right, what is that made of?
That is concrete. And then keep hitting the wrong thing. In each of these, there's a metal kind of interface. And then this is actually, if you were in the vault, right, the canisters are stored sort of in those tubes. And then...
So they're not totally down in there?
No.
They kind of sit on top?
There's I don't think I have the right picture in my slides. Yeah, so there's two canisters in that location. The bottom canister really sort of rests on the floor. The second canister rests on top of the bottom canister. You can see that there's kind of a air path there at the bottom and at the top, so that as they're stored, that helps. And there's sort of a natural, you can kind of see the way the airflow works is air comes in this side of the building, goes through the vault, and then sort of through the chimney, so to speak. So there's a natural air current through there that's helping to take heat away.
So as a non-technical person, of course, my mind goes to spontaneous combustion, but there's not any kind of material that can happen, that can happen with, right?
No, so I don't, there's really nothing in that vault other than concrete and steel. Gotcha. And then there are, on the upper section of the vault where you can drive the canister transporter, there are controls there for making sure you don't leave flammable materials. Kind of generally, all of our areas have controls so that you don't pile a bunch of combustible material someplace where it could catch on fire.
Thank you.
Okay. We'll come back to this side of the table and go to
Sade Shofidia, SRS tab. Thank you for your presentation. Will you please describe the sampling methods for quality?
Say that again.
Will you please describe the sampling methods for quality?
So Melissa is going to talk about the lab later, so she will probably cover this in more depth. But generally speaking, each of the vessels, the SRS, the SME, have a path where a sample, the contents of that tank can be sampled by pumping it to the lab, where there's sort of a recirculation line. And then within the lab, there's a tap, so to speak. Melissa will explain this way better, that you draw a very small sample, and then that sample is segmented out into a series of samples. Each of those are analyzed. There's normally, more than one set of analysis done on each of the samples, so that you can do a statistical analysis and confirm that you got a good sample result. Not sure if that got you far enough.
Yes, I'll inquire with Melissa for elaboration on the analysis.
She's going to cover what we do in the lab, so she'll, I think, touch on that. She's thinking about it right now.
Thank you. Will you please describe the decontamination process?
Okay, so again, it's a little bit like a touchless car wash, if you can imagine that. So it's a bunch of spray nozzles so the canister is as the canisters are moved from one cell to another within the process, there's a series of grapples that pick up the canisters and move them from place to place. The decontamination is done by taking a canister on a grapple that's kind of specialized, so it can turn, move the canister up and down in a particular sequence. The canister is then lowered into a tank that has a kind of a frame where there's a series of spray nozzles. So this is what I'm saying. It's kind of like when you go into the car wash and there's 100 spray nozzles spraying your car. There's a set of spray nozzles that are designed to cover each area of the canister. So, and as it's being sprayed, the canister's turned, lifted. There's different sequences in which nozzles are turned on at what time, so that you're washing the canister from top to bottom. But the decontamination sort of in and of itself at the canister level, coming out of that spray nozzle, is both water and frit, which is basically like sand. And so the impact of it's kind of like sandblasting. So the impact of the sand on the canister metal then takes a very thin layer off that will remove any of the contamination that could be adhered to the canister. Once it goes through that entire sequence, canisters then move to a position where we confirm by sort of wiping different spots on the canister and then checking the cloth that we use to wipe to confirm there's no contamination. If there was, then that canister would get sent back and go through another cycle. If it's not, if we don't find contamination, then it moves forward to the next step.
Thank you. I know that your goal is to produce 300 canisters a year. Is that correct?
Yeah, on average, that's about what we need to do for the rest of the mission. If you look at it's about.
What are we currently producing per year?
So we've had a pretty wide variety of canister production. A lot of our years have been in the 250 to 275 range. In the last couple of years, we've been at lower production rates as we've brought SWPF online. So we had some downtime that was generally associated with that. Introducing a new plant, making sure everything's working together. So we've had, I think, years that have been like 50 to 70 cans. We've had a pretty wide variety. When you look at our, we've produced 300 cans in a calendar year. it's a challenging goal for us, but again, the plant was designed to be able to do that. So we got work to do to get there, but we've demonstrated that the plant in and of itself has the capability. We need to be able to keep it up and running.
What is the plan to address the deficit canister production?
So there's a couple things. I think Mike mentioned yesterday that part of the improvements that we've implemented so far are to give us sprint capacity, so that when we are up, we can operate at a faster rate. As we're going on, we're replacing components that we found to be unreliable, that have caused us to be down. We're buying more spare parts for that. We are continuing to look each week. We do an analysis of, what are the things that stop us in production or have slowed us down. So there's a number of changing things that could occur. But the primary things we're seeing right now is we've got to keep the plant up. So we have equipment that's failed that we're replacing, equipment that may be obsolete that we're replacing. We're buying new components to have set up as spares. And if you looked at the plan, there's a little bit of an ascension curve to get to the max rate. So we're not immediately trying to go from 80 cans to 300 cans next year, but each step along the way gets us there. And then our next big set of improvements will be next spring when we implement upgrades to our crane system and upgrades for strip effluent being able to be stored in another tank as well as transferred into both the shroud or the SME.
Okay, so with those anticipated updates, what number of canisters do you anticipate producing annually?
Again,
Projected number?
yeah, so we'll get to on average 300 cans a year. Like I said, I think the next year is maybe closer to 200, and then after that, the plan is to get to 300. There's variations each year depending on what's going on.
We'll have to probably make those up in the out years. I mean, spread them out. That's to get to where we need to be to close in 2037. There's also some initiatives taking place to help maximize how much we load in a can. So hopefully that'll drive a little bit of those canister counts down that we projected in our system plan.
Curious about the life cycle of the melter. The melter.
Yeah, so so generally we plan on a melter lasting about 10 years. I'm trying to remember now
I think the longest one ran for about 14 years, if I'm not mistaken. The other one was maybe 8 years.
Yeah, so we had about 15 years almost for the longest melter. Our plan is about every 10 years we should be ready to replace them. So part of the overall plan for the mission includes a melter replacement in about 2030.
So we already have a melter 4 already stored and ready to get replaced if we need it. If melter 3 goes down, we'll have a backup for that. We already have it. They're working on melter 5 fabrication as of right now, if we need one by then. Hopefully not, but that's the plan.
Yeah. Will you please describe the anticipated outage for April 2025?
Yeah. Go ahead. Well, for April 2025, there's a bunch going on. I think they're planning to replace the cross-flow filters and SWPF. On the DWPF side, we're going to implement the lag storage, which will give us SWPF about another week. Basically another week. If DWPF goes down, they have another week to process until they're held up. They also have the SEF to SME initiative going on, which will allow us to take strip effluent from SWPF and divert it to the SME. So we'll have the flexibility to send that to the Strat or the SME. That'll provide some process flexibility. Do you want to add anything to that?
Yeah, there'll be other sort of more routine outage activities. Each of the plants has preventive maintenance things that we'll do. Those are the big mod type improvements that are planned for the outage.
Essentially, it's like planned downtime.
Yeah.
To make improvements.
For a couple for a couple weeks at least. It's the big outage that we have planned typically. I know that Mike and Joel had mentioned sometimes we may have a fall outage that's a little bit smaller, but typically, all the facilities work together during that time. They try and pack as much as they can into that downtime because everything is down, right? No processing. So, the goal is to basically get as much done as you can within that time frame. And so a lot of that would be like the process improvement initiatives that we talked to you with the Climate 9.
Thank you.
Okay. Don?
Don Colson, CAB Nuclear Materials. What's the moisture content of the slurry as it goes into the melter?
It's a little. I'll have to get back with you, Don. If it's lost from my head. It's about 48% solids, but
it's going to steam off in the process.
there is some steam that comes out in the melter. There is moisture going into the melter.
And that's going to be captured and recycled in some way.
Yes. So each of the vessels has an off-gas system on it. The one for the melter is a little bit more complicated. So the off gases, including that vapor, get collected. It goes into a tank. There's a number of tanks where we're collecting similar things from different vessels. All of that eventually goes into a single recycle stream that goes back to the tank farm.
All right, I think you said the frit is a borosilicate.
It is, yes.
Is that chosen because of the strength and weight of the glass it'll produce?
I'd say it's really more of a chemistry. It's the best glass for encapsulating the waste, making sure that the waste can't leach out. To some extent, the strength of the glass isn't that important in terms of ensuring that the radioactive material doesn't get out of the glass.
Thank you.
There are strength requirements, but mostly chemistry.
Okay. We'll cut across the room to Hubert.
Thank you, Hubert Von Tool, CAB. I have two questions about the double stacking. Double stacking, you're taking a canister, you're putting a 2.5-ton canister on top of it, and if my arithmetic is right, that means that the floor goes from supporting a design weight of about 6,000 tons to over 12,000 tons. Could you address the safety of this issue?
Yeah. So any of our modifications goes through a process where we evaluate the impacts on the rest of the system. So I don't have the specific loading in my head in terms of the double stack, but as part of that process for double stacking, we evaluate the structural load, how much weight can the floor hold, the thermal load, can the air remove the heat that it's supposed to, the radiation dose, have I invalidated the shielding because we've added. The process addresses all of those items. And so before we move forward with double stack, that was addressed. So we'll say overall the canister transporter is a lot more weight than any of the canister loading in and of itself. So the structure of the building is very robust. and that additional loading from the canister's been evaluated and is within the design.
Thank you. My second question, the film, I thought this was kind of funny. The film said that by not building another storage building, we saved $100 million, which sounds great, but the film never mentioned how much all this process actually costs. Now, this may not be a fair question to ask you, so feel free to put, but what's a good source on what this whole process is actually costing?
On the process for modifying the buildings for double stack, or for the process for the overall process? I don't know.
A couple million.
So each of the, I'm not sure where the best source of data is. Each of the facilities has an annual budget. You can sort of sum all that up for the contract cost, and I'm not sure exactly where we are right at the moment. It's, it's hundreds. For DWPF, it's a couple $100 million a year. I think Jim's going to help me out.
Yeah, hi, Jim Polk, DOE. So our overall liquid waste budget is about $1 billion a year. And so, again, there are some incremental costs of transporting and moving some canisters around, but very small compared to a capital cost of $100 million.
Pat?
Pat Kilroy, on the cab. This is my first year. Got plenty of questions, but how much nuclear waste from other sources than SRC are coming in to SRC in 2024?
The amount of waste that we receive, so kind of overall flow sheet, the tank farms receive waste from the canyons. Tank farm is still receiving a small amount of waste from the canyons each year. Not sure the best way to quantify that for you. It's so if we're trying to process 9 million gallons a year of salt out of the process, the amount of waste that we receive from the canyons is more like a couple 100,000 gallons, just to give you some perspective.
Pat, are you asking if it's coming from
Off-site.
Okay.
Off-site.
That's a different answer.
Yeah, so again, from sort of my scope of the world, the only waste we're receiving is coming from the canyons.
So there is no off-site nuclear waste coming into SRC.
Yeah, Jim Polk again. So what Doug is trying to express here is, what we do in our system planning is we assume from a liquid waste perspective solely, okay, 300,000 gallons, up to 300,000 gallons a year comes over from nuclear materials. Now, the source of that, again, the nuclear materials program still receives material from different locations, different, research reactors and so forth. So, as you follow the bouncing ball down the road, right, there could be some atoms or whatever coming from some of that fuel. But again, what we deal with in the liquid waste program is up to 300,000 gallons. But in the form of any liquid nuclear waste or things like that, we don't receive anything like that on site. No.
So South Carolina receives no nuclear waste from off-site, period.
It receives spent nuclear fuel from different locations.
Okay,
No,
okay.
That's not waste.
right.
Okay, spent nuclear fuel eventually has to be processed. And so it's either going to be vitrified, put in tanks or something, correct? So the thing I keep going back to, I see this line where we're going to close down in 13 years. And there's a plan to make so many canisters. And here we are, but here we have additional stuff coming in that are outside the perimeter of SRC. So how can we make plans to say, I'm going to build this many canisters and I'm going to be finished by this date? Or how can we do this when we know we're going to make 80 pits this year, right? And I assume there'll be some remnants of waste from that.
Yeah, so first,
So how can we go on and say, we've got this plan, but we still got stuff coming in? And we don't, and y'all probably don't know how much we're going to get this year, or next year, or 5 years from now.
no, okay, first, there is, the NSA organization is responsible for fuel to be received on site. They have a very good understanding of what's coming in from any of those sources. Sources from domestic research reactors, we certainly have a very good understanding what that may be. Now, what we have to do is separate the programs, right? The liquid waste program, by definition, we are to a closeout program by 2037, we finish our job. The nuclear materials side of the house or NSA side of the house, they may still have material coming in, but the process will be they have to define how that material will be handled in the future. It could be a dry storage system, it could be alternate processing, whatever it is, but in the year 2034, we sever that tie between the nuclear materials organization and the liquid waste organization. So I finish my job on liquid waste. The nuclear materials side has the future planning responsibility to sort out what happens with any nuclear material that may be received after that point in time.
See, I don't understand, going back to the 2016 agreement, with the state and the DOD, we're supposed to get rid of the 11.5 million tons of plutonium that's at the site. So if that's going to be gone by 2037.
No, you're confusing two. That material, that plutonium, does not come over to the liquid waste program. That'll be dispositioned by other ways.
Okay.
So 2037 is the liquid waste program, finishing up, closing up the tanks, vitrifying the material we have, and we'll be done.
The agreement, I thought, was 10.5, well, it was 10.5 tons.
But again, disposition of plutonium has nothing to do with the liquid waste program. That'll be dispositioned through alternate means.
So we could continue on accepting nuclear waste here and processing it past 2035?
That program, again, is outside the EM purview. NSA will disposition any material it gets after that point in time. It won't be coming through the liquid waste program.
Okay. All right.
And this is Amy. I just want to clarify too. I did phone a friend to make sure, because we don't have the nuclear materials folks in the room today. Since we're talking liquid waste. So the only other waste that we receive on site is from naval reactors. It is not liquid waste, and it goes to the E area low-level waste facility. So just to reiterate what Jim is saying is we don't receive liquid waste from other sites.
Okay. So we don't receive any nuclear waste from other sites?
No, we don't. We receive nuclear materials from other sites. And that's a very different thing. We can talk about that offline if you like.
Oh,
but
okay.
Yeah, it's two different things.
Because, I look at nuclear waste, what is it, this concentration, and then if it's nuclear material, it's this concentration. Is that what we're looking at?
Yeah.
It's not that pedantic of a difference. There are, where it's headed and what's being used for, there's lots of differences that go into those definitional differences.
Okay.
And just to reiterate, the return of spent nuclear fuel and all of that to the Savannah River site is an NNSA thing. So we would need to get the right people in the room to make sure you're getting the correct answer. I know enough to be dangerous.
The other question I had, are we going to have to build additional buildings to put the canisters in eventually?
No, the two buildings that we have now will support all the canisters that we'll make.
Okay, how does vitrification do on mercury?
There's, within the chemical processing part, within the SRS, there is mercury that is evolved and collected as part of the SRS processing. So the concentration of mercury that goes forward to the glass is small. And again, as we look at a qualification for a sludge batch, part of that qualification is to ensure that everything is encapsulated in the waste, including the mercury.
Thank you. You had a great presentation.
Thanks.
And John.
John Thomas, CAB. Thank you for the presentation. My question is around the actual tank, because you got the salt and the sludge in the same tank. How do you know when you're done with the salt and you're moving on to the sludge?
So I spent a lot of time in the tank farm, so I'll go ahead and take a stab at this. The way the salt and sludge were generated in the tank farm is a little bit different. So typically, as material came out of the canyon, that was an acidic process. There was metals there. When we neutralized or made that waste stream caustic, those metals became metal hydroxides. That's what forms the sludge. So in the generic tank farm process, waste from the cane was received in certain tanks. Those tanks have a sludge layer. Typically, those tanks do not have a hard salt layer on top of them. Once the solids settled in that sludge tank so that you had sort of clear liquid, that clear liquid was then transferred to a tank where it was processed through an evaporator. So the overheads, the vapor stream from the evaporator goes to ETF, and then the concentrated stream goes to a different waste tank. In that different waste tank, as the salt solution cools, then you get the salt cake. So normally, there's always an exception, but normally the hard salt cake and sludge are in separate tanks. There are tanks that have both, and they're in a couple different configurations, but generally the process for doing salt removal is basically adding water and mixing. When you get done with that, there are solids that may settle out that did not dissolve. That then basically becomes part of the heel and sort of gets treated like sludge. So to some extent, when you're doing salt removal, you'll dissolve everything you can, and whatever is left basically will get treated like sludge in terms of how you're going to go through the next step in the process. So at a high level, there's not that, our picture is a little bit deceiving. There's not a bunch of tanks that have a sludge layer and a hard salt cake layer. Typically those are separate based on how we did the processing. There are a couple tanks that do have both, and basically you'll add enough water to dissolve the salt, you'll transfer that out. When you get to that point that you have sludge left, then you'll treat it like a sludge tank, adding water mixing pumps to suspend it.
And I guess my question was, at what point do I know that I've just taken out the salt and all that's left is sludge?
You'll basically get to a point where, the addition of water is not putting any more salt into solution. You're done with salt dissolution at that point. Okay. When we do salt dissolution in preparation for sending that to SWPF, part of that involves not sending solids to SWPF. So there are checks as we transfer dissolved salt out of the tanks to make sure that we're not transferring solids.
Okay.
So there's generally, you're going to add enough water that the salt dissolves. You'll know you're not doing any good with just water anymore. You'll transfer the clear part of that, the part without solids, basically by setting where the pump is. and then after that, you'll just treat the rest like it's sludge.
Okay, all right. Let's see. There were a couple areas in your presentation you talked about water evaporation. And the question is there any radioactivity in that evaporation?
There's always a little bit. So generally, the boiling process is pretty good at separating radionuclides. So they have to get captured in a droplet that gets carried forward for them to go. So there's typically part of the boiling process, you get a pretty good decontamination of the vapor. It's not ever perfect. So when we collect all that vapor that condenses as part of our process and send it back to the tank farm as recycle, it is radioactive. There is radioactive material in that stream that goes back. And then it goes back into the tank farm and it gets, again, it can get used for dissolving salt. It may go through another evaporator where there's additional separation. Ultimately, if you took everything to the farthest extreme, the water eventually gets to the effluent treatment facility where it's treated for the small amount of contamination that's left.
Okay, so the evaporation you're talking about is not released into the air, it's within
No,
the process.
No. Each of the vessels. So, not shown on our wonderful picture, there is a condenser that sits on top of the vessel. So when you're boiling, the vapor stream goes through a condenser. It's cooled, it condenses, that condensed liquid gets collected in a tank. Non-condensables that would go through the condenser then go to a ventilation system. And ultimately the air in the ventilation system goes through a sand filter. But the vapor from boiling goes through a condenser, it's condensed, it gets collected in a tank in DWPF. Those tanks then get consolidated in a recycle tank in DWPF, and then eventually are sent from that recycle tank back to the tank farm.
Okay. All right. Let's see. The water spray, so you talked about the nozzles and the water spray on the canisters. What happens to that water? Isn't it contaminated because you've cleaned the canisters?
It is. So that
wiped off the contamination.
Yeah, the water from decontaminating the canisters is collected. It is transferred to the SME vessel as part of adding frit into the SME. So part of the decontamination of the canisters uses frit to be abrasive. The frit and the water from that are collected and ultimately get transferred into the SME vessel, where again there's boiling that occurs in the SME, goes through a condenser, gets collected.
Okay, and then verifying that it isn't contaminated any longer does not sound very scientific, just to wipe a couple areas.
Everything we do is scientific. So before we got to the point where we could do that, as part of the demonstration of the DWPF process, there was a lot of testing that was done to determine that swiping not every bit of the canister represented swiping the whole canister. So in the beginning, everything got swiped. We eventually built enough data to say, hey, statistically, if we check these certain points, that's representative of checking the whole canister.
Okay. Let's see. Oh, the heat of those canisters. How are you monitoring the heat once it's in the storage area? So
there's a couple things that are done as part of that. One is before, when we make the Schrat batch, and the SME. We know how much radioactive material is going in there, so we know ahead of time, before we ever make the canister, that we're going to be within the limits for the can, so that it won't get too hot. Within that building itself, there are temperature measurements that are taken, but in general, before we ever make the canister, we know how much radioactive material is going to go into it, and that's within the bounds of what's acceptable to be stored.
Okay, but didn't you say you were monitoring the heat in the storage area?
Yes, we got belt and suspenders. We're always going to check that things are happening the way we think they are.
Okay.
And we check, there's, the residual sort of thermal temperature from the glass cooling, that gets checked before the canisters get moved through the process as well. Make sure it's cooled enough that as it goes through the process, it's not causing issues.
Okay. My final question then is around the federal decision about the repository. Who's to say that this is not the is that considered one of the possibilities?
It's safe where it is. For a long time.
That's all I had. Thank you.
All right, and Candace, wrap it up for us.
I sure will. Candace Cage, Cab. I do have a few questions. So in the video, it referred to intermittent storage. In your presentation, you said temporary storage. Is there a reason why those two words differ? Because those are two different words.
Yeah,
They have two different meanings in my mind.
Yeah, so I think, let me make sure I heard, I think the video says interim, interim, not intermittent. Okay, and temporary. So yeah, we see those as the same. That's not the federal repository.
Gotcha. Okay, so does DOE have an official definition of permanent, temporary, or interim storage?
Again, I'm going to kind of stick with Amy. There's decisions to be made. I think in the storage there is language that describes what permanent storage is, but that's
But not temporary or interim? Because normally temporary has a limit. There's a time limit on temporary things. Okay, so my next question, when was the first canister put into storage?
DWPF started up in April of '96, so that time period.
Okay, 96. All right, and so my last question is, will the shielded canister transporter also be used to remove the canisters when there is a permanent storage solution? Or do you have to build something to remove them from the current location?
There's probably something that will have to be built in order to load the canisters into a transportation cask. The SCT, the shielded canister transporter, is not specifically built for that. Not to say that as part of that process, you might not just figure out how to use it in a different way, but there will have to be some kind of loading facility built in order to be able to get the canisters into transportation casks for them to be moved to the repository.
Thank you.
All right. Brittany, Doug, thank y'all so much. Okay. I know that we are a little bit over, and by a little I mean a lot, but that's okay. We always recover our time. But I think we need to take a short break because it's been a little while anyway. So let's take 10 minutes. We're going to come back at 10:40, not 10:41, not 10:40 and 30 seconds. Back in your seats, ready to go at 10:40. most of us are back. Y'all want to get started a tiny bit early? You ready? Okay. One quick announcement. Edwin had a family emergency he needed to go tend to, so Jim Folk has graciously agreed to step up since we're going to make it easier for him to help answer questions anyway. Up next, we've got SWPF. I think y'all are really going to enjoy this one. I know that I did during the dry run, so I think you're going to appreciate the information coming from this set of presenters. Jason and Steve, y'all ready? Yeah. Let's go.
Good morning. My name is Jason McIntyre. I'm the Federal Program Manager for Salt Waste Processing Facility and the Saltstone Production Facility. This is my first cab. Really impressed with the astute questions you guys have been asking and the intellectual curiosity. Just to reorient you, you've been talking about our sister facility, DWPF, Defense Waste Processing Facility. SWPF is kind of the enabler. We're taking the material from the waste, from the tank farms, we're taking the waste, and we're separating it to get it into those two inherently safe waste forms, the glass and the grout. And SWPF is kind of the new kid on the block, came online in 2021. And as we brought it online, Steve and his folks have found new ways to improve it and make it more efficient. And I'm going to hand this off to Steve and let him tell you about some of those things that he's done.
Okay. Good morning. Thank you. Thank you, Jason. Again, I'm Steve Heil. I'm the project director at the Salt Waste Processing Facility and in-stream delivery facilities. I'm excited to be here today to talk to you about the things we have going on and the great work our team's doing. So without further ado, we'll jump right in. So first couple of slides are going to be a bit of a refresher for you, but I wanted to reiterate some of the things specific to SWPF on these slides. So as you recall from seeing this slide a couple of times now, this depicts the volume of waste remaining to be processed. Key things here to note over on the far left, over 90% of that waste is salt waste, which is our mission to disposition that waste. And then of course it contains about, as shown here on the right side, about 50% of the radioactivity. So that's a big mission. If you notice the pictures on the right, we've talked a bit about the constituents of the various layers in the tank. So just to reiterate, the salt cake, as you see in the top picture there, it is very much like you would expect. Good thing I brought my lunch bag here, because if you think about salt, just think about salt, just like this canister I got from Costco a little bit ago, right? Although our salt has radioactivity in it, but in a physical form, it's very similar. This is waste that's been in the tank for some period of time. It is either purposely or over time dehydrated, and so a good bit of it is actually crystallized out into salt crystals that are not dramatically different than typical salt. Now, our challenge is to clean these tanks out, we have to get this into a form where we can remove it from the tanks. So one of the key things the tank farm does is they add liquid to rehydrate this salt, just as you would in your kitchen to dissolve the salt in the solution. So that 30 million gallons of salt waste there, once we've added liquid to rehydrate it, to get it in a form where we can transfer it out of the tanks, it's going to make we estimate about 100 million gallons of salt waste. So really that is the mission of SWPF, is to take that 100 million gallons of salt waste and process it for final disposition. So again, you've seen this slide before, but just to reiterate, here in the middle is the salt waste processing facility. I kind of like to think of SWPF as being the hub at the center of the spoke, because again, 90+% of the volume of waste will pass through SWPF over the life of our mission. You see in orange, it depicts the various streams, and as shown in the bottom right here, our inputs, as you've already heard numerous times, come from the tank farm. So they collect a recipe of material from these various tanks into about 1 million gallon batches. We call that a salt batch. So each of those salt batches is sampled, is characterized by Melissa and her team, you're going to hear this later today, to make sure that it meets all of our waste acceptance criteria and it's going to process satisfactorily, et cetera. And then they transfer it over to us in about 25,000 gallon batches. So we get each batch, we receive about 25,000 gallons. And so within our facility, we do two primary purposes. One is to segregate out the most highly radioactive waste, and that material as shown here, makes its way over to DWPF that Doug just spoke about and gets vitrified into the glass for long-term safe storage. And then in the end, the resulting material that's now been decontaminated, we call it decontaminated salt solution, actually makes its way over to the salt production facilities and the salt disposal units. And you're going to hear more about those units this afternoon, but that's where the final resting place is for the decontaminated solution. Again, SWPF is a one-of-a-kind facility, the only kind, certainly the only one in the United States. And let me tell you a little bit about, now I've told you what we do, let me tell you a little bit about how we do it. So it's a very complex facility, but really it comes down to a few programmatic steps that allow us to accomplish that mission. As I said earlier, we received the material from the tank farm, and in the first couple of steps here, we perform a chemical addition. Monosodium titanate is a chemical we add. Monosodium titanate, MST, as we like to call it for short, is a bonding agent. So we add that material in those 25,000 gallon batches. We let it agitate, mix up, and then we let it sit there for about 12 hours and let chemistry do its thing. And so what the MST does is it actually bonds, forms a chemical bond with actinides, things like strontium, uranium, plutonium. The actinide series or group of atoms are attracted to that MST, and it actually forms a solid material. And then we pass that solid material through filters. And the filter, just as a filter does whether it be in your automobile oil system or in your HVAC system, it filters out contaminants or solids. So some of that material passes through the filter, which would be, right on the right button here, which passes through is the filtrate, the liquid. It goes on to the next step of the process, and then the solids that are captured through those filters are captured in batches and transferred over to DWPF again for glass vitrification. Now that stream that passes through the filters to here goes through a second chemical process called solvent extraction. I'm going to tell you a little bit more about those in some coming slides. But in solvent extraction, we chemically separate out the cesium primarily, which is the main radioactive constituent that resides at this point. We separate out the cesium, and likewise, the cesium gets transferred over to DWPF. And then the resultant stream, which is a decontaminated salt solution, makes its way over the salt storm for that final disposal there. So that's kind of high level what we do, not only what we do, but how we do it. So a little bit more about the processes that are involved with that, the two main processes, the filtration process and the solvent extraction. So in that first filter process, after we've added that monosodium titanate and we let it go through the 12-hour period to let chemistry do its thing, we began to press it through these very large filters. Just to give you some idea, these are some photos. A photo of the filter insert on the left, kind of a schematic of how it's laid out on the right. But these filters currently are about 10 feet tall. We have 3 of these filters. Each is 10 feet tall. It has about 234 tubes inside it. And this is actually a 2-foot cutaway of one of those 10-foot tubes. And I'm going to pass it around. And I have old eyes, but you're going to have to take my word on it, I think. But there are 0.1 micron holes or pores in this tube. So I'm going to pass it around, and I'm going to challenge any of you to point a hole out. And if you can do that, you win the door prize for today. So take a look at that. Okay. So again, so the way it works there's 234 of these 10-foot tubes inside each of those filters. We pump the material into there. It has a back pressure valve, essentially, that regulates pressure. So it's about 80 pounds per square inch inside that tube. So we're trying to press liquid through the walls of that tube. And if you can see from the construction of that, that's a pretty hefty challenge because it's not as simple as passing through your HVAC filter or your oil filter perhaps in your vehicle. It is not, no. Thanks for the clarification. I should have had a disclaimer early on. No, it is not. It's actually a freshly fabricated tube right out of the shop. So once that material, again, we press it through that filter, those very large filters. Again, the solids that have the MST and the actinides now can't pass through those 0.1 micron holes, so they're captured on the inside of the tubes. The liquid passes on through the tubes, and it has cesium left in it, and then it goes on to the next step. And then periodically, we clean the inside of those tubes, which captures all those solids out, and we transfer that over to DWPF. So that's kind of at a high level how that process works. But hopefully the visual there gives you some idea of the challenge of pressing lots of material through that. I like to say the material weeps through the tubes because it's hard for me to imagine a 20 gallon per minute stream flowing through there, given the small holes. Okay, so the next step of the process, at this point we've removed the actinides. We have a liquid solution that still has cesium, soluble cesium in it in a liquid form. So the way we remove that is through a process called caustic side solvent extraction, CSSX. We like to use a lot of acronyms if you hadn't figured that out yet. But, so I'll try to define them when I use them. If I don't, call me out. So basically, the CSSX process is 36 of these very complicated mixer cellular units. The picture on the left actually shows the bank. You can see it goes lengthwise there. So that is a mixer cellular unit there. It basically has a motor on top and some instrumentation. Down here in the bottom, it has a bowl, as we like to call it, our mixing area. And again, it's a very complicated, highly engineered piece of equipment, but the principle it operates on is very simple. Again, good thing I brought my lunch bag. Because if you think about your salad dressing, right, oil and vinegar, same process here. We put each one of those 36 centrifugal contactors has 2 inlets to it. So one stream that comes in is a liquid of one density. The other stream that comes in is a liquid of a second density. One's heavier than the other, just like this salad dressing, right? When it sets over time, it will, by forces of nature, by physics, by gravity, whatever, phase separate because of the different densities or different weights of the solution. However, if I give it a little mechanical agitation, those 2 will mix, as they do here. And if I leave this here for, 30 minutes or so, gravity would do its thing again, physics would do its thing, and it will separate. If we waited 30 minutes for it to separate every time, we'd never make 2037. So what we do, these contactors, they have a mixing section where we bring the 2 streams together. They spin at very high speed. They spin at up to 2,400 revolutions per minute. And so they're spinning very fast. In addition to mixing, as the fluid moves up that bowl, it's spinning very fast. Now, think about riding the merry-go-round. What happens when you ride the merry-go-round? The faster you go, what happens? It tends to want to throw you off, right? Or in my case, when I take my kids to the fair and we ride one of those spinning things, I have younger grandkids, I always want to make sure I sit on the outside because I'm a big boy. I have a lot of mass. And so the heavier mass even has more force, right? So the same thing happens inside this bowl. The heavy material collects on the outside, the lighter material is held on the inside. Each of those has a small opening that lets the material escape and move on to the next stage. So that's a simple, I'm a visual learner, so I hope you don't mind my elementary age, but it helps I think, visualize the way it works. Simple engineering processes in a very complicated device. So after 36 mixing and separations, we control the flow ratios, we control the chemistry going in, coming out, the temperature, all those variables we control. And by doing that, we can very accurately predict what's going to come out on the other end. So what's going to come out on the other end when we do that process right, we're going to have one stream that is loaded up with all the cesium in it, and then the other stream is going to now be essentially fully decontaminated. So the cesium stream goes on to DWPF for glass vitrification because it's the highly radioactive material. And now we've got this clean stream that's now being removed of actinides and cesium, and it makes its way over to the saltstone facility in Rodney. He's going to tell you all about that later this afternoon and how we do final disposal of it there. So, all right, that's a little bit about not only what we do, but how we do it. I think this will be helpful when I talk about some of the optimizations. Okay. So where are we kind of on our report card? As I mentioned earlier, SWPF is a fairly new facility. It kind of completed the the mission capability at Savannah River site to disposition our liquid waste. It is a first-of-a-kind facility, so there's obviously some learning that goes into that. This is kind of a graphic you've seen likewise other places, but to me, it's a couple things. One, it's a report card, or how are we doing against our goal? And then secondly, it shows the massive amounts of tweaks and adjustments that we've made along that roadway. So if you start in the bottom left over here, in year one, which is back in 2022, year one processed about 2 million gallons. So that was kind of a starting point. First year of operation, going through startup, learning, et cetera. Since that time period, over the last 2.5 years, here we are mid-2024, currently we're operating pretty consistently in a rate here between 5 and 6 million gallons per year. We're pretty consistently over recent months operating 400,000 to 500,000 gallons a month, pretty consistently, which will equate over the course of a year to 5 to 6 million gallons. So we're climbing up this curve. The things above the green line here, there are about 25 items, give or take there, I believe. Some of them are small incremental things, some of them are larger step things, but collectively, those continuous improvement things are what have allowed us to get from 2 million gallons a year to now we're right at approaching 6 million gallons per year. And I'll talk more about these later, but we've got another 8 or 10 things that we have planned over the next year or so that we have high confidence is going to step us from the 6 million range up to our peak performance level, which is about 9 million. So there's been a lot of automobile analogies used in the previous presentation, so I was thinking this morning, how can I continue that theme? So I'll say it this way. Think about SWPF as a brand new prototypical race car, right? It's a brand new race car. And it's got a lot of horsepower. Just by design and putting the right transmission and the right motor and suspension and all together in one package, it's got a tremendous amount of potential and horsepower. But what does it take to make that car run up front on race day? You got a carburetor adjustment guy, you got a suspension guy, you got an air pressure guy. Everybody's working together, right, to make little tweaks and fine tunings to collectively find a sweet spot where it operates at peak performance. And I kind of equate that a little bit to what we're doing at SWPF. We've got a machine that has a tremendous amount of horsepower and capability. We're just delving into that. We're making some of those fine-tuned adjustments that eventually will allow us to get to the peak performance. All right, so what have been our challenges today? Well, two major things. The first one has been no surprise. The biggest challenge we've had today, and really our limiting factor, is how fast we can weep or press material through these small holes or small pores in these filters. That's been our greatest challenge. Secondly, once the material passes through there and gets over into the solvent extraction process, we've had some problem with precipitation or with solids forming. Remember I told you in those contactors, once the material is kind of separated in that bowl, there's a small opening for the heavier material to escape and a small opening in the center for the lighter material to escape. But those are pretty small holes. If it were too large, it wouldn't work, right? Everything would just blow out. So you have to have the perfect size hole to make all that process work. And those holes, some of them will tend to plug over time if you get solids precipitating in there or solids hold up. So that's been a secondary problem we've had. So I want to take the next couple of slides and tell you about some of the key things on that climb to 9 chart that we've done to address these things that has allowed us to climb up. So first of all, again, this is our 234 tube filter insert shown over here on the right side. And so the original plant design recognized that periodically you would need to backflush or clean these filters just as you would a pool filter in your pool at home, right? Periodically you have to backflush it, clean it. And so the original plant design had that flush material being sent back to the front end of the plant to go back into the feed tank. Now what do you think happened there? Well, a small portion of that material had the opportunity to reaccumulate back on the filter. So we were getting some recycle. And so we operated enough to prove that it was more than originally estimated. It was significant enough to where it was impeding our process significantly enough. We pursued a process change. So we worked with our sister facility, DWPF, because they were going to be the recipient of this material. We studied it on their end to make sure it's going to be no adverse impact to their processing parameters, regulatory requirements, et cetera. And we got a process change in place. So now when we clean those filters, we collect that material, and rather than feeding it back into the process, we go ahead and send it straight on to DWPF where it can go into their glass vitrification process. And so that has allowed our filters to operate much more efficiently as one item. Another thing we've done around the filters is we reduced that MST concentration by 75%. And that sounds like a large amount, and it is. With all processes, particularly in the nuclear business, we always want to make sure we have very conservative safety margins or margin in there. And so as you would expect, when we started the plant up, we started with a very large margin of MST. We were adding about 400 milligrams per liter. After we operated some time, we collected data, we did some lab testing, and we were able to prove that we could get similar efficiency or similar performance out of the filters by reducing that all the way down to 100 milligrams per liter. And we're still well within regulatory limits. That was briefed to obviously our customer and to our regulators to get their buy-in before we did this. But again, it's made a massive change. So if you remember back to the description, the MST and the actinides form a solid. Of course, the solids are what have to be collected in these tubes. So just by common logic, right? Less MST means less solids, which means the filters perform better or easier. So that was a big change for us. And oh, by the way, we got a secondary benefit out of this one as well. I remember I mentioned we were getting some fouling or some solids built up in some of those contactor holes or weirs. And we were able to capture some of that for sample analysis. And what we found is those solids had a fair amount of titanium in it. So, of course, we began to look, well, where could the titanium be coming from? Well, the only real source for titanium in our process is the MST, the monosodium titanate. So, in effect, by reducing the MST on the front end, we got a secondary benefit of less solids generating material, in our solvent extraction. So we got a twofer with that one. Okay. A second one, kind of moving on now to solvent extraction. Again, I'm just highlighting a handful of those 25 or so items we've done. This one involves cleaning. So after 36 solvent extraction cycles there where this stuff is mixed and settled, these mixer settler contactors are very efficient. However, no machine is 100% efficient, right? So even after 36 of those, on the tail end, there's still a minuscule amount of solvent sometimes entrained in that liquid. And downstream, we don't want to send solvent over to Doug at DWPF because that causes him some process problems. So we have these devices called coalescers between solvent extraction and the material we send him. A coalescer basically is it's a fancy term for a tank that has a filter mesh inlet. And so as the material passes through that filter mesh, these fine droplets, very fine droplets of solvent tend to collect on that mesh material and separate them out of the rest of the stream that can safely go into DWPF. Well, one of the problems we've been having is, in addition to catching those fine droplets of organics or solvent on those filter mesh elements, we're also capturing some solids. And so the solids block flow, which presents a problem for us, obviously. So we would have to shut down and do a cleaning process, an acid cleaning process to run fresh acid through there and regenerate or refresh those coalescer filter elements and then start back up. Well, the plant wasn't really initially set up to do that easily. So in order to do that, we'd have to shut the whole solvent extraction process down, get all our right chemical setup done, introduce the acid, let it do it washing, et cetera, and start the plant back up. And that took normally about 2 days, about 4 shifts. We have 12-hour shifts. That's about 48 hours or 2 days to do that. And we were having to do that pretty routinely. In fact, at times as much as once a week. So out of every 7 days, we were losing 2 days just to go in and do these coalescer flushes. So that was very impactful to our throughput. So we put our minds together and thought, well, how can we improve that? So we did a plant modification during one of these planned outages to go in and add an additional chemical line or two. And essentially what it allowed us to do is, without shutting the solvent extraction process down, we can very briefly, from about 2-hour period, divert 1 or 2 of the streams, introduce acid, clean the filter, and put it right back online. So essentially what was taking us 2 days now takes us about 2 hours. And so that has vastly improved our throughput. Obviously, the more time you operate, the more throughput, right? So that was a big one for us. All right. Another one in the solvent area and solvent extraction area is around solvent recovery. Like most tanks or most facilities, we have a tank or a sump area that collects kind of miscellaneous stuff. That's pretty typical in any industrial setting. We have a tank, it's called the solvent drain tank, and it's kind of a catch-all tank. When we occasionally have to drain heels out of tanks or out of lines to do maintenance or other work, it drains to this drain tank. And so what happens over time is you kind of get a mixture of stuff in there, and what we have found is over time, because you got a mixture of stuff in there, sometimes it may cause solids, it may cause odd stuff to happen that it's not a safety hazard, but it's a processing hazard because they have some solids in it or something like that that make it difficult to process. Now, again, eventually we have to clean that tank out, and the way the system's set up, that material goes back into the process line. And again, that would mean another avenue by which we are reintroducing solids or contaminants back into our process. So we put our minds together and thought, how can we resolve that? Some really nice radiological work here inside our hot cell within our laboratory, and Melissa's going to share more about the laboratory later today. But inside our hot cell there, where we only do remote work with manipulators, there was a filter that existed. And so we came up with a concept by doing about 14 pipe cuts and modifications in there, we could reroute that stream through this filter so that we could filter it and remove the bulk solids before we put it back in the process. So just to give you some idea, this is one of the more highly dose areas within our facility. So when we came up with this idea, the biggest hurdle was not 14 pipe cuts and wells. We do that kind of stuff all the time. The biggest challenge was it was inside a hot cell that's not designed for human occupancy, and the dose rate in there was 25 rem, which is, for those of you that know, that's a pretty high dose, right? The federal limit is 5 rem per year, and so it was 25 rem per hour there, so in way less than an hour, you could have picked up the federal dose limit. So we knew it was going to take some innovative work to do that. So again, we put a team together. They came up with ways to flush the lines, decontaminate, put some shielding in place, et cetera. And so through the efforts of that, we were able to reduce that by 99%, from 25 rem down to 0.2 rem per hour rate. And so that was a safe rate to go in and do the work. And we had some craftsmen go in and actually make those pipe modifications for us. And that has paid off huge dividends. Again, this is maybe a little bit of an eye chart, but if you have a handout, but hopefully you can at least see the trend. If you see the blue line at the top, that was during a previous solvent recovery where we were emptying that tank. When we put it back into the system, the differential pressure is being measured in certain places, and that was the differential pressure where solids were plugging the system. So you can see it made a huge difference. We're adding a lot of solids to the system, and then recently after we did the modification, the kind of gold line there reflects that same instrument, but now we're putting the material back in with way less solids because it's been filtered, and you can see there's very little change in the differential pressure. So this one was easy to measure, and it gave an immediate benefit. All right. So that's like I say, 5 or so, 6 of the things out of those 25 that we've actually completed. I want to tell you also about a handful of the really important ones we have upcoming. So Doug touched on this, and so did Mike yesterday. So no secret that one of the easiest ways to improve throughput is to improve time online, right? The more downtime we have, that's lost opportunity. So we're doing everything we can to improve our plant reliability and availability to keep it online as much as we can. Some of the things I shared with you there, like the improved coil ester flushing, cut a 2-hour day down to a 2-hour evolution. So obviously that made a vast improvement in our throughput. So we're looking at a lot of other things. One of the key things for us in SWPF is spare equipment as well, specifically contactors. Some of these contactors, they're moving pieces of equipment like any moving piece of equipment. They have bearings and other things that occasionally fail, so we do have to change them out. And then with some of the solids issues, occasionally we have to change them out just so that we can take them out and do more aggressive cleaning methods and replace them. So we originally only had 4 contactors. Shortly after that first year of operation, we issued a large procurement for 16 more units. We just received those a couple months ago. Again, these are one-of-a-kind, kind of specially engineered, fabricated units, so it's not something you just go buy off the shelf. So it took some time to have them fabricated and tested and put together, but we just received those. So now we have 20 spare units, which is more than half of the 36 we have. So now when we have planned outages like we plan to have in the spring, we can go in and do pretty massive replacements just for preventive reasons, and then take those 20 units out and be refurbishing those for the next major planned outage. So that vastly decreases our likelihood of having a failure while we're trying to operate. Probably the next, I'd say the biggest step change thing we have planned is, as I told you earlier, right now our critical point is getting the material through these tubes. So we've done a lot of things, the way we do the flushing, the way we do the cleaning, I described a couple of those earlier, that have made big improvement. Let us go from 2 million a year to almost 6. But to get from 6 to 9, it's going to take something additional. And so the something additional that we've come up with is we're going to vastly increase the size of these filters. Right now, each filter has about 234 tubes, and they're about 10 feet tall. Well, we've had our design folks look at it, and they've come up with a new design. We're going to be able to take it from 10 feet to 16 feet, and from 234 tubes up to 288. So the combination of that is going to give us about double the surface area. So we're going to have about twice the surface area. And so, again, probably won't be exactly one-for-one improvement because there's some hydraulic changes and other things that go with changing the size. But essentially, we're going to double the size capacity of our filters, which should give us a major flow change. So whereas we're getting consistently 16 to 18 gallons per minute now, we expect that to go well up into the 20s easily. So that was going to be a major change for us. Again, those units are being fabricated right now by off-site vendors. They're actually making more of these tubes and getting them all put together and tested for us. We expect to have those units on site early next calendar year, January, February, March. We should receive one about each month there. And during the planned outage, planned to start in April, we're going to install those and restart with a much greater filtration capacity. Another thing is, this is another thing we've been testing in the plant. We call it filter aid. Those of you that are my age or older, you may remember the Pepto-Bismol commercial. When I think of filter aid, this is what I think of. A little humorous, but to me, but if you remember the commercial used to come on, it shows your gastrointestinal tract, and then all of a sudden you see the pink stuff just kind of flow through there and coat, soothe, and relieve. Okay, that's what I think of filter aid, right? And so, obviously there's an engineered reason why we have 0.1 micron holes in this, right? But what we have found happens in reality in the facility is the very, very fine, small particles, they will embed in the 0.1 micron hole. And because it's high pressure, they get deeply embedded in those pores, in those holes, and they block it. So actually, it's better to have bigger solids than smaller solids because the smaller ones get down in the pore and actually block the hole. The big ones tend to collect on the wall on the inside, so periodically we can flush those off and filter's good. So filter aid is an additive we add to it that's an engineered additive that is the right size particulate, so it doesn't go down in the pores. It kind of coats, soothes, and relieves the pore so that the other stuff will flow through. Does that make sense? Okay. All right. So we've been testing that. We just completed a second run in the plant. We're gathering all the data. So later this summer, we're going to come out with an official position on that to see if the additional cost and the impact of adding it provides a meaningful benefit. But that's just another example of some of the innovation we're doing. And last one I'll mention here is increased sodium molarity. So again, this is a little bit of trial and error in the plant, but it's been very successful. It was our plan all along to do it, but we've incrementally done it in a systematic way to prove what we can do and still be within our waste acceptance criteria. So when this salt is redissolved over in the tank form, they aim for a certain molarity of sodium concentration. The base plant design was 5.6 molar of sodium. We felt like we could go higher than that and still be safe. And so when the material comes over to us in SWPF, originally we were having to add more dilution material to adjust it down to 5.6, which is our baseline input, because it's coming from the tank farm higher than that. So we've systematically over time raised that, did some testing, and we're currently operating at 6.5, 6.7 molar sodium, still getting the same performance out of the plant, or better really in some cases. And so the net result of that is we're having to add 10% less dilution material on the front end. So again, 10% less dilution means 10% more through the plant, right? So that's, again, been a pretty good step change for us. So we'll continue to monitor that, and if there's opportunity, we'll seek even raising that even higher perhaps in the future. All right, so I said a lot of stuff there, kind of fast, but if I had to leave a couple things I'd like for you to walk away from is these couple of things. One is, from year one of startup, 2 million gallons per year. Remember that ramp-up curve? We're operating today roughly 6 million gallon per year rate. We're confident we can do that pretty consistently now. We got a few things that we're working that I described to you, like these increased filters, that over the next year or so should put us up in the 9 million per gallon per year range, which according to our 2037 plan is about the peak performance we would ever need during that 2037 execution period. So we're well off the ramp, and we got a plan to get there in the next year or so. All right. Any closing thoughts, Jason?
No, you did great.
Okay. All right. Open up for questions.
Phyllis, we'll start with you.
Phyllis Britt Cab, just have one question because I appreciate it. I'm beginning to understand.
Yeah.
It's taken a long time. Anyway, I don't know exactly how part of this process works, but when you were talking about the hot cell labs and the changes that you've made,
Yeah.
Did you ever actually have to put humans in it when it was 25 rem per hour?
No, ma'am, no. We would never do that, no.
Okay, you
That's all.
could measure it other ways without.
Yeah, we have remote dosimeters and things we can put in there to measure the dose rate, and so that's what we did. And it's physically blocked, so no human can get in there until we intentionally mean to.
And what would you have done if you couldn't reduce it?
Well, we're a pretty innovative group. We use robotics, we use extended tools, we use things like that. So there are other spaces we have been into with the facility where we used, a robotic tool or device or something like that. So we would have probably come up with something like that. But in this case, given the number of cuts and all we needed to make, if we could humanly enter, it was going to be the most efficient way to do it.
Gotcha.
Yep.
Thank you.
Mm-hmm.
Okay. Pat.
First of all, that was really fantastic.
Thank you.
A couple of questions. The actinides, I assume they're pre-treated to make them into larger molecules or whatever. Is that what the titanate does?
Well, again, this is chemistry. It's kind of a little bit of magic that happens in the solution. But I mean, the plutonium, uranium, the actinides come to us as is, right? They come to us as is. The monosodium titanate, because of its electrical, chemical, electron configuration, et cetera, it has an affinity to attract those. So it's a chemistry thing. If you think back to elementary chemical, it's a bonding agent. So they chemically bond and stay together.
So it binds before it goes to the filters?
Correct.
Correct.
Yeah.
Going through the whole process, and even your centrifugal, what's the percentage of the actinides, the plutonium, uranium that get through there?
Oh, it's very, very low. Less than 1%.
Less than 1%?
Well less, yeah.
Okay.
Yeah.
So then, processing further, it would go to sludge or salt dome and...
That's correct, yeah. Once those actinides are separated out, they're collected into, we call it a batch, we use that term a lot, but they're collected into a tank, they're sampled, make sure that it meets DWPF spec, and then we transfer it over to DWPF.
So there's a minimum amount of plutonium and uranium in the sludge or the salt dome.
That's right. And in the salt material, there's not a lot of plutonium and uranium. I don't want to mislead you. It's not, the majority of that tends to reside in the sludge, but there is some plutonium, uranium, and other actinides.
But it is there.
It is there, correct.
Okay. The other thing, how in the heck do they drill those holes in that pipe?
Well, that's a good question. They don't drill holes. This is sintered metal, it's called. So actually, they have a powder. I've never watched it, but I've had it described to me. The fabricator makes these by taking a powdered metal and they have a mold of some type. They put the powder in the mold and then they press it at very high pressure and temperature. So it forms a solid here. But on average, you know, they've done enough testing to know if they put this volume of material in there, press it at a certain volume, at a certain temperature, on average, there are 0.1 micron holes in this. So pretty neat engineering.
Yeah. Thank you.
Yeah.
That is really cool.
Yeah.
Sade?
Sade Shofidia, cab. I'm curious about how long has the CSSX been in place, and how often are they replaced?
The contactors, the contactors,
Yes.
the centrifugal contactors. Well, you know, that technology has been around a long time. Other places on the site, the canyons use centrifugal contactors, so that technology has been around since the 40s or 50s, 1940s or 50s, so, you know, going on 100 years.
One?
But the specific ones we use, they're particularly sized and particularly set up for our specific application. So there was a pilot or a small scale unit that was done over an H-tank farm, you know, in the mid 2000s to 2005 to 15 time period. I may not be exactly, but in that time period. So they use these contactors, and so what we have is just a further development of those. So they've been used in this specific application, to my knowledge, for 20 years maybe. But again, in our plant just really started up in 2021. So I'm not sure I answered your question.
Thank you. But what percentage of the solids are reduced with the CSX?
It's not so much about, well, at this point, there's a very, very small amount of solids going. There's essentially no solids going into CSSX. What happens is, as it goes through that process, there's certain places where there's chemistry changes between acidic and basic material. And what we have found after studying it for a couple of years now, it's really at those transition points where we typically have the solids. So the material coming into CSSX has virtually no solids in it. However, when it goes through some of those pH swings, or from acidic to basic swings, occasionally a little bit of material will precipitate out. Solids will be formed as part of that chemistry change. And that's where we've had the problem. So we're attacking it a couple different ways. We're trying to attack it from a chemistry adjustment, as well as better flushing and whatever techniques. We're kind of going at it from both sides of the equation.
How do we know that it's an added benefit, that it's actually a reduction in solids if we're not measuring the amount of solids?
Well, the purpose of solvent extraction is not to remove solids, it's to remove cesium, so that the material coming out is cesium-free and free of radioactive material. And we do measure that. We have strategic sample points along the process, and then our final products are heavily sampled, and Melissa and her stout team perform analysis to make sure that it does meet our process specs, as well as our regulatory limits, and et cetera. So that is definitely confirmed.
Thank you.
Okay.
Any other questions or comments from around the table? Seeing none. Gentlemen, thank y'all.
Thank you.
Thank you.
So there are 2 time slots on the agenda that you never really want to have, and one is before lunch and the other one's after lunch. But I don't think you're really going to have to feel bad for Rodney about this, because this is another one where I watched the dry run, and I think you guys are really going to like it. And I think you've been enjoying these so far. There's been lots of positive feedback. So without further ado, now that Rodney's behind me, I'm going to step out of the way. Sir?
All right, very good. I appreciate that. All right, just for in-stream delivery, about 2 years ago, I got a chance to come to the cab and describe what we plan to do with in-stream delivery as an organization and the facilities we were going to bring together. So I'm glad to be able to come back today and talk about what we've done and some of the challenges that you'll see as we go through the presentation that we're working, just like everyone else that's been up here. We're working our way on that climb to 9, and we've got a role to play in that. And so we'll talk about those challenges, and obviously improving reliability and continuous improvements for us is very important for us. You've seen this slide before. For in-stream delivery, we're the tail end of the process, and that name in-stream, we took that from the oil and gas industry. So if you know anything about that, so the front end upstream is where exploration and finding the product is made. Midstream is where it gets processed, the refineries and so forth. And then the in-stream is how it gets delivered and distributed out to the customers. So we kind of took that same mindset. So for us, tank farms is kind of our upstream, and then the two facilities you've already heard about this morning for SWPF and DWPF are that midstream, and then we get the low-level side of the product coming out of these two. And so low-level comes to us either in the form going to DSS, the decontaminated salt solution, coming to our production facility, or then the effluent treatment facility, ETF, takes the water side and is a water treatment facility, and then releases that clean water out to the environment. So when we looked at how we could gain some efficiencies here between these two facilities for ETF and Saltstone, one of the things that we realized in building that reliability, we had complementary operational cadence. What I mean by that is for ETF, they typically, when they were standalone, they would run a few days at a time, 24 hours a day. For Saltstone, we could run a few hours at a time, and we could actually shut down in between the runs, the way the two operational facilities work. Now, obviously, as we get into that climb to 9, we want Saltstone to be operating much longer periods of time. But at one time in our history, Saltstone was actually basically a Monday through Thursday kind of operation. We'd run days and we could shut down. Over on the ETF side, you had an operational crew that, because they had to run several days at a time, 24 hours a day, they had a crew that was staffed and trained to operate that facility all that time. By bringing the two together, then we got efficiencies in our staffing that allowed the operators to be trained on both facilities, qualified on both facilities, and then we can use that operational cadence to gain that efficiency for both facilities. And then finally, organizationally, we brought together ESD, the operations, under SWPF organizationally. So Steve, that you just heard from, that's my boss. And so he's the director over both of these facilities, as well as SWPF. And so what he provides for us is that support organization. So while operations is kind of standalone, maintenance is standalone with ESD, all of the other types of support that we need to operate those facilities, that comes out of SWPF and Steve's organization over there. All right, so let's talk about ETF and its mission. So treating wastewater to meet the discharge limits, safely reduce those, get that water treated so that it can be released. It's a permitted facility. You've got 3 photos here from various angles of the facility, and it's a standard industrial wastewater treatment type facility. So anything that you would find at another industry or heavy industry, you're likely to find a very similar process to this. There's nothing overly special about what we do. For Saltstone, now that mission is to take the decontaminated salt solution and get it into the grout. And that's the long-term storage solution for, and again, it's decontaminated, very, very low waste remains in that DSS stream when it comes to us. The 3 facilities on the bottom, SWPF is our input to us, and then the production facility is the center photo on the bottom. It's where we mix the liquid waste with dry feeds, and it's very much like a concrete batch plant. You can think of it in those terms. Obviously, we have to deal with radiological concerns, and we've built a process room to do that. But it's in general, liquid waste comes in, dry feeds, mix it up, and you've got a grout process that then goes out and gets pumped out to the SDUs in the bottom right there. So I'll walk us through the process of saltstone itself. The dry feeds come to us by trucks. The most prominent feature when you see our saltstone facility are the silos. They're about 120 feet tall at the top. There's 4 of those silos. They hold about 450 tons of dry feeds material each. They're about 5 stories tall at the very top there. In the metal framing work that you see underneath, we have blenders that blend the material and weigh it out and blend it, and so that we get the right recipe mix of the dry feeds. And that recipe has had a lot of evaluations done through the labs over the years, but that's not a recipe that changes very much. I mean, it's changed one time in the 5 or 6 years that I've been there, and I'll describe that to you here in a minute. So it's not like it's changing recipes. It's just you want to get the 2 constituents that we're currently using in the right mix and then go forward. In this top right photo, this is actually inside our process room, and you'll see this metal box here that kind of comes, it looks long, rectangular metal box. That's our mixer. It's in our process here, and that really is the heart of the process for saltstone. So on the back side, kind of difficult to see, but the round gray pipe that you see there, large round pipe there, that's where the dry feeds come in. And then they're inside this box, there's 2 shafts with augers that bring the material forward, and then the liquid waste is dropped in on top, and then the mixing takes place right in that area. From that box then, on this end, the material drops down into our grout hopper. And the grout hopper is about 300 gallons at a time, and then that material then, it's already fully mixed by the time it gets to the hopper, so then it just feeds down to the grout pump. This pump is has 2 heads on it. The large round areas are the heads, and you see that it's a peristaltic pump. And if you want to understand a peristaltic pump, if you think about your tube of toothpaste and you grab it and you squeeze it and you go all the way to the end, that's a peristaltic action. And so it's pushing that material out. And each one of those heads has a hose inside it that gets squeezed by some rotors on the inside of that head, and that pushes the grout material out then to the SDUs, obviously through piping and valves and so forth. So that's the internals to the process for saltstone. As we look at our optimization challenges prior to SWPF coming online, we had processed at a production rate that subsequent to it coming online, we've doubled and close to tripled that amount of production on an annual basis. And so we've still got a little bit of a climb there to get to 9, about a 3x improvement from where we are today. And we've got a series of improvements that I'll go through here and show you how we'll get ourselves to that higher rate. The first one, and Mike alluded to this yesterday in his presentation, but the first one is how do we transfer material into saltstone? And so obviously SWPF is our source of input, and then we also have the tank farm and tank 50, and this is the most common way that we bring the DSS to saltstone right now. So I'm going to show you 2 ways to do it. One involves taking it up to the tank farms to tank 50. When I say up, there is a very slight hill, slight rise between these 3 facilities. And so if you can think of the transfer lines as a street or a one-way street, there's a one-way street that comes out of SWPF, and it can take a turn and go up the hill to tank 50 in the tank farms. And that's our most common route to date. So we line up and SWPF sends the material to tank 50 DSS. This provides the greatest decoupling of the facility. If I need to do maintenance work in saltstone, I don't want to shut down SWPF for my maintenance work. So they can send material up to tank 50. There's capacity for it there. And then I can do my maintenance work, be ready to come back online, and then we kind of get to step 2, which is the next slide there. And step 2 then brings that material back from tank 50 all the way down to me, okay? And obviously we're valved in such a way it wouldn't go back toward SWPF. So this, when we use this method, and this is the way we've historically done it most frequently, when we use that method, it puts the most traffic on that highway. So if you think about, I've got to send material to tank 50, and then I got to bring it back out of tank 50 to get it to me. And as we climb the climb to 9, then that traffic gets pretty busy on that highway. And so our second alternative, and this is the improvement, is a direct transfer. And the direct transfer just takes it straight from SWPF, puts it into the front end of saltstone. Now for saltstone, we have 2 input tanks on the front end that can take roughly 2 batches apiece from SWPF. So I'm talking about 2 to 3 days worth of, if I had my front end completely empty and I'm bringing material in from SWPF, I can let SWPF run 2 or 3 days before my front end is full and I have to process that, okay? That requires that basically one of their output tanks comes to one of my input tanks, and then the next day or the next time we do a transfer, we alternate back and forth, all right? So as long as both facilities are up and running well, that neither one of us need to do maintenance and so forth, we can get that and we can make that work, and then that'll really make us go much more efficient in the days ahead. And we've done this several times to this point. The next item that we did and the benefit we had in bringing ETF and saltstone together was a control room consolidation. And what this allowed us to do is we control both facilities from one control room. We can use a single shift manager in order to be able to control both facilities. And in this photo, these computer screens you see on the front end are the workstations for saltstone. The ones that are in the back, and that's been cut off a little bit, there's several stations back there. They have stations for ETF, and so an operator is assigned to work in one facility or the other for a given shift, and we rotate the operators through based on their qualifications. And then that allowed us to, in the organization, then we got dedicated maintenance and support staff for both facilities. And again, it's that complementary operational cadence. So one facility needs to run, we'll run it. The other one needs to run, we'll run it. And we can adjust them back and forth. To date, we've not run them both at the same time in the control room. We'll get to the place that we'll do that. We've not done that yet. And then finally, we are adding a simulator for ETF. ETF had never had a simulator, but we're adding it to our saltstone simulator. All right, the next improvement involves how we deal with that mixer. And the mixer, where the dry feeds and the liquid waste comes together, you can imagine how abrasive that is at that point, and it wears the mixer out. We can process approximately 2 million gallons through that, and then we're going to have to take our mixer down for repairs and refurbishment. So the top picture on the right is at the end of about 2 million gallons going through the mixer. And kind of you can see some of the wear there on the paddles and the augers. And then on the bottom picture is where the liquid comes in after we've done a repair and a refurbishment on the mixer. So historically, that mixer has been repaired in place in the process room. To do that took us about 2 weeks. 299H is a facility that we have. It's a machine shop that can handle contaminated equipment. And so what we've been able to do is we take the mixer that's in the process that's getting worn down, and we can take it out. We put the spare mixer in place, hook it up, and then we're back into production while we take that spare mixer to 299H and then refurbish it there. And it's actually much easier for the maintenance folks to work on it in the machine shop where they've got more space, they've got the tools and equipment that were always kind of tight to do in the process room. And so basically using the crane, we can fly it in and out. And we've got a greater than 50% reduction, and we'll get faster as we get more experience at doing that. We've done this once thus far, and the next time will probably be this fall for that rebuild. All right, the next improvement we have is the dry feed delivery system, and working with our vendors. The dry feeds come to us via truck. We built a new parking lot for trucks that are full to come in there. That's what you see in this picture. And the vendor worked with us and gave us a lead driver. So the first truck of the day, he shows up, and then he spends the day basically moving the trucks that arrive, moving them in and offloading them to the silos that you see here in the picture. And then we have another parking lot where the empties go. And so between that lead driver and then a number of other drivers, we'll get those trucks in throughout a processing day. And we need roughly one truck an hour while we're processing in order to be able to continue our production. Obviously, we've got a lot of capacity in those silos, so we can run several days without any truck deliveries. But that has sped us up quite a bit, getting our dry feeds taken care of. And then the next slide are upgrades that we did to the dry feeds. Inside the silos themselves, at the bottom, there's a cone. And in that cone, the walls of that cone have a membrane where the dry feeds material rests on that membrane. We can actually pump air into that to kind of give a little motive force to the dry feeds. And so then it falls by gravity. Once we open the valve, then it'll fall by gravity. And so we replaced the membranes. That was the first time in 20 years, so we may not need to replace the membranes again in the life cycle that's left. If we do, we'll do maybe one more. And then we added new air compressors that deal with that system, did some repiping that made it more efficient. And so right now, today, we can unload 3 trucks simultaneously. We do have some modifications underway that allow us to unload 4 trucks. And I'll talk about on the next slide here kind of how that sequence works. So approximately 2 years ago, we transitioned from a cement operation where we had cement as a part of our mixture to a non-cement mixture, which is what we use today. So the old that you see there in the blue, we had slag, fly ash, and cement. And the mixture was a 45-45-10 mixture. And so we had 45% was slag, 45% fly ash, and 10% cement. In early testing, this is testing done probably back in the 90s, they identified through that testing that we could have cement anywhere from 0 to 10%. And at some point along the way, 10% was selected. As we got into and looking at, well, what else can we do here with the equipment that we have, there was additional testing done by the labs, and they identified that a 60-40 mix had virtually the same properties that the earlier mix had. And with those properties being what we needed, it also allowed us to take a spare silo that was there in case we had a equipment failure and put that into operation. And so this is now the new configuration where 2 of our silos have fly ash and 2 have slag. And we run a 60-40 mix, but 60% slag and a 40% fly ash. I'll take just a moment to explain those 2 products for you. So slag is a byproduct that comes from blast furnace. So if you think of steel manufacturing, the big blast furnaces that they have, slag is a byproduct of that. It's used commonly in cement type work, concrete type work. So you'll see both slag and fly ash that are very common in the industry. Fly ash is a byproduct of burning coal, so coal-fired plants generally provide the place that the fly ash would come from. And again, having two mixtures makes it more simple, as well as gives us additional capacity in our silos. All right, this last slide then is just one of our continuous improvement items. Like some of these facilities you've seen before us, we don't have a lot of dual trains. We have a single pass through our process. And so as we go through that single process, if anything breaks or wears out, I've got to stop processing in order to get in and to fix it. So we developed what we call our process critical equipment list, and I've given you some examples here on the right-hand side. Each of these little face plates deal with one of those particular devices in the process. And the important point for you here is at the top, we've gathered data on runtime. How much processing can we do before we would expect this piece of equipment to either degrade or to break? When it breaks, of course, now I can't produce, and so I need to go in and I need to repair it and get it back into service. For us to go in and repair an item, there's three main things that we have to have, and that's these three items down here on the bottom. I have to have a work package that the maintenance crew can use to follow to safely do the work. I have to have a lockout that removes any energy, whether it's electrical, process, pressure, steam, anything like that. I have to lock it out so it's safe for the maintenance team to go in and do the work. And then finally, our material service requests, we got to have the spare parts to do the repair. So what this process allows us to do is we can look ahead, we can kind of get a feel for how are we doing relative to our historical operational time on a given piece of equipment? And if that piece of equipment were to break or degrade right now, am I ready to go with these three items? And so you may see, if we pulled some others up, this is a kind of a red-green process. Either I have my parts in hand or I don't. So if I didn't have my parts, I'd see a red. And I have the ability with this computer screen to go in and see how the health of my system and see what I need to do if a component starts to wear out. Am I ready to go to make that change? And then what that allows us to do is we're kind of like a pit stop in an auto race. You know, the car comes in, people jump on it, they get it done, and then they get back to racing. That's kind of what that allows us to do, to be able to continue to process. So my takeaways for you are we want to reduce risks, and we do it in a safe fashion. We've combined two facilities together to gain some efficiencies. We're using that power as one. We're increasing the overall reliability as well as continuous improvement items in order to meet the mission and be on that climb to 9. All right.
All right, folks. Questions, comments from around the table? Hubert, let's start with yours.
I apologize for slipping in a question right before lunch. About the control rooms.
Yes, sir.
Who in the control room has authority to stop a process if they see a problem developing?
Any operator would have that authority to stop. Obviously, the full authority for operations relies with the shift operations manager, but any operator, and I've been in many of our morning job briefings in the morning and pre-job briefs, and every time our shift managers say anyone can stop if they need to. Yeah.
And just to highlight, that's site-wide.
Yeah.
That is a site-wide policy.
Yeah.
Pat?
Yeah, one quick question. You're telling me now that the grout is just slag and fly ash?
That's the two dry feeds components. Obviously, the DSS comes in there as well. That the picture of the mixer, the liquid feed comes in this pipe right here. It's kind of a yellow pipe. Comes in. Yeah,
Okay,
that's
so
where
that's where the cement comes in.
Well, yeah, the dry feeds come in first, and then the liquid waste comes in on top of that, and then gets mixed in the mixer.
Okay, the liquid waste.
Right.
And so the liquid waste and the slag and the fly ash make up the grout.
Grout, that's correct. You got it. Yes,
Thank you.
sir. Okay.
Okay. Sade?
I would like to ascertain the 299 H mixer rebuilds, they're complete? Or is that something you're intending to do?
We've done our first one,
Okay.
and we got a second one that's, we'll actually get started on the one that we've pulled out for the second one in the next week or two. Yeah.
Cool. And curious about what is the projected implementation, like completion of the ESD simulator that's adding the ETF model?
Yeah, that's by the end of the calendar year, this year.
Yeah.
Very good.
Phyllis?
Phyllis Britt, CAB. I had two quick questions. One, as you have cross-trained operators, has that reduced staff or has it increased production? I mean, increased the speed of the process?
Yeah. So what we were able to do is we didn't decrease staff, we didn't increase staff. We kept the staff that we had. It did allow us, and it's on one of the slides there, it did allow us not to hire for a fourth shift for Saltstone. But basically we stayed at, once we identified that's how we wanted to go, we stayed at that staffing level. Yeah.
And my second question was about coal. As this process continues, we're not using coal anymore, right?
Well, what we get is a byproduct of burning coal. So that comes from, primarily, it comes from coal-fired power plants. But we get that byproduct. We aren't getting coal or doing anything with coal ourselves.
Okay, so not on site, we're getting that from elsewhere.
That's right, that's right. It's just a product we buy. Mhm.
Thank you.
Yes, ma'am.
Appreciate it.
Okay.
Okay. Any other questions, comments, concerns from around the table? Saying none. Rodney, thank you.
Thank you. James.
All right, folks. See you at 11:52. If we round a little bit, let's make it 1:30 back in our seats. Don't make me regret giving you the extra 8 minutes. Everybody have a good lunch? Nice break? You ready to rock and roll again? All right. Melissa, you ready?
Good afternoon. My name is Melissa Santalla Ramos, and I'm the manager for SRMC Laboratories. During our presentation today, you heard a lot about the laboratories, so I'm going to talk about what the labs do, our mission, how we support SRMC. So SRMC Laboratories, we have 3 laboratories for SRMC. We have one located at the Salt Waste Processing Facility, one at the Defense Waste Processing Facility, and one at the Effluent Treatment Facility. These labs, once SWPF merged into SRMC, we brought all the labs under one umbrella, unifying our overall capabilities. What did that bring us? That allowed us to expand our range of analytical capabilities. Now within the labs united as a whole, we have a lot of different instrumentation that we can utilize or resources for SRMC as a whole. We've standardized our laboratory practices in our qualification program. We onboard lab technicians, and now as we unified together, they all come in, they take a core class all together, they go through that initial qualification program, and then they go and get designated to their facilities. And once they're in their facilities, they get some specific facility training as well. And it also allowed us to take advantage of our specialized technical expertise across SRMC. We have a lot of scientists, very talented, knowledgeable scientists within the laboratories, and now we're able to utilize that knowledge and capability for SRMC as a whole. What is our mission? What does a lab do? So I have this little diagram here on the back side, on the bottom, where it shows kind of like a blood work. You know, when you go get blood work, they take a sample. And then when you go back for your results, you get a report. And that report gives you different levels, right? It gives you levels of your cholesterol, levels of your iron, glucose. That's what the lab does. It takes samples from the different tanks, and it analyzes them, and it provides a report. And that report gives, like engineering and operations, the different constituent levels that are in that sample representing that tank. So the labs, they perform routine analysis for process samples. We talked about today that different parts of the process, there's different tanks, and we run analysis to ensure that that process is working well, that it's what the constituents in those tanks are as expected. We do sampling analysis to support troubleshooting. If something's not going well in the process, lab samples does analysis, and engineering utilizes that data to be able to troubleshoot and find a path forward. Verify inline process monitoring instruments. We do special studies. I know you heard Steve talk about some of our solid studies that we do, and we determined that some of the solids that were in the process were based in titanium. Lab did a lot of those studies as well. And then product verification. And the next slide, we're going to talk a little bit more about product verification, but Steve mentioned that SWPF, through their process, developed 3 streams. Well, we verify that stream before it can be transferred out. Doug mentioned that different parts of the process, we have to check different levels to make sure we can verify the quality of the glass. Lab does that product verification. So SWPF Laboratory, we ensure that the 3 product streams comply with the process requirements of the downstream facilities before transferring. There's one stream that goes to saltstone. We do analysis on that stream. We take a sample from the tank, do analysis, and provide that report to saltstone to make sure that it meets their requirements to be able to accept that. And we can't transfer until they have that report. They analyze that data and make sure it meets their requirements. Same thing with the other 2 streams. We have a sludge stream and we have a strip effluent stream that goes to DWPF. And we also provide a report of different levels of constituents within those streams before they can be transferred to DWPF. And DWPF Laboratory, we verify the quality of the final glass product for long-term storage requirements are met. I know Doug mentioned that there's different part of the process where we sample to make sure that when we go to the SME tank that product performs and can create good glass. We actually take a sample of that tank. We make it in lab scale into glass, then we crush that glass and perform analysis to make sure that the glass that's actually going to be produced in the melter meets our final product quality, that it will make good glass. ETF laboratory, we verify the removal of chemical or radioactive contaminants of processed water. And we do a lot of analysis of low-level radioactive waste from F and H tank farms. You know, I did mention that SWPF, DWPF, and ETF have laboratories. Saltstone does not, and tank farm, however, ETF does quite a few analysis for F and H tank farms. And then for Saltstone, we already do that analysis of their stream before it's transferred from SWPF to Saltstone. So they use that for quality analysis. And when we also, for Saltstone and tank farm, SRMC Laboratories also supports. We mentioned about the salt batch qualification. That's the stream that goes into SWPF for processing. SWPF does that salt batch qualification. We get a sample from the tank farm. We do analysis, about 49 analytes on that report, and we make sure that we qualify that batch before it comes to SWPF. And then I put there Savannah River National Laboratory. They're a big key of our support for SRMC. They do a lot of analysis for SRMC, especially for the tank farm and for Saltstone, and for the other facilities. Sometimes we have special studies that we need, special analysis. They've done a lot of analysis on solids for SWPF. They do a lot of analysis on sludge for DWPF. They have a lot of capabilities, like research capabilities, that we don't have internally. So they do support us quite a bit, and we do send a lot of samples to them for analysis. Now, with SWPF came online, laboratories, we did bring also some additional analytical capabilities that SRMC did not have in the past, and we're trying to internalize some of that scope. So some of those samples, we are currently evaluating different samples that we sent to Savannah River National Lab to be able to internalize them. But we can't, people ask, why can't you do all of them? Well, the primary support of the lab is support the facility. We're a supporting organization, and we need to make sure that we can support the operational side. If we talked about we need to do the qualification on certain tanks before they get transferred, so that's our priority, because if we cannot provide that analysis on a timely manner, then the facilities can't move forward in their process. So our priority will always be supporting the process and getting those tanks qualified to be able to move forward. So the SRMC laboratories, we provide 24/7 support. We have 4 rotating shifts in a day group. We have about 100 laboratory personnel. And about 70 of them are technicians. We initially ramped up our staffing, and that's to be able to support the climb to 9. As we ramp up the throughput, as the facilities run quicker, we will get samples more frequent. So to be able to support that ramp up of throughput, we ramped up our staffing. Our laboratory technicians go through a very extensive training program. We hire people, most of our lab technicians will hire locally. They range from people who just finished their science degrees, people who worked in different industries within the surrounding of the CRSA. And we have some that this is like their first professional job. They just graduated high school, they're trying to develop a career, and this is their first professional job. We provide them a very thorough training. They train for almost a year before they go on shift and provide support. That training constitutes safety practices. First thing they learn is how to work safe and what are our protocols that we have in place to make sure that they can work safely. They learn laboratory fundamentals. A large percentage, I would say probably 90% of the people that we hire have never worked in a lab before. So we teach them the basics. What's a beaker? What's a pipette? What are instrumentations? And then we teach them how to use our instruments. We have very high-tech analytical instrumentation. We teach them the chemistry behind it, the fundamentals of what that instrument does and how it works. Then we teach them how to operate the instrument. And then we teach them how to prepare the samples to put on the instrument. Now, I do like, our analytical instruments, they're not specialized for SRS. These are instruments that are used in labs worldwide, in the pharmaceutical industry, in the chemical processing industry, even in the academic industry. So the lab technicians, especially those early in their career, and they're trying to develop a career for the future, they will get trained on every single piece of equipment, and it does help them build that resume and a skill set that they can use as they progress in their career, not only at SRS. Continuing training. So not only do we teach them the basics, when they come in, they train about a year before they can actually do work. We continually train them. We develop training to just give them a refresher on what they've learned. We give them training on lessons learned throughout the facilities as well. So they're continuously learning, and that helps them also develop their career. Here we have a little table of samples analyzed from 2022 to current. And if you look at, we have about, I divide them by analytes. What are analytes? We talked about that report that you get when you get your blood work, and there's different levels, right? There's like cholesterol, iron, glucose. Each one of those are considered analytes, and you get a level of what that analyte is. So if you look at our table, we've done, overall over 30,000 analytes since 2022. And why do I break it up by analytes and not samples? Well, analytes, each one of those represents a person who had to go and prepare the sample and put it on the instrument. Sometimes for one sample, we have 20 analytes, and each 20 of those analytes is a different preparation. So it's a different person, a different instrument, and that's resource management there. And kind of gives you a really good view of how busy our workload is. Safety. So obviously, we're going to focus the next few slides on safety. And we're going to focus on the different engineering controls, the different controls that have been designed into the lab to keep our workers safe. To make sure, because they do work hands-on day to day on rheological material, with chemicals. So we're going to talk about how do we keep them and minimize exposure to chemicals, to rheological material, and for contamination control. Here's a list of a few of the things that we're going to talk about. I'll talk about it more thorough as we go through the slides. Cells and manipulators. I know you guys heard the word cells a few times today. Glove box, samplers, radio hoods, fume hoods, and radio benches. And you can see one of our technicians there working in a glove box, and we'll talk a little bit more further regarding each one of those. So this is our cells and manipulators. So what is a cell? If you look on the left-hand side, you see four windows. Each one of those windows is called a cell. And what the cell does, it has a window, and you see those little robotic arms that each one has a set of two for each one. So that window is kind of like a room. And in front of that, in there, we perform different actions. And those robotic arms, called manipulators, that's how we remotely handle highly radioactive sample. And what those manipulators do is that, you see one of the technicians on the right side holding one. As they move those manipulators, there's some hands in the inside, and I'll show you a picture in the next slide, that mimics your movements. And that's how we protect ourselves from rheological material, right? In this case, we have distance and we have shielding. And you'll see at DWPF, we have about 7 cells, and at SWPF, we have 4. Why do we have more at DWPF? Because we do a lot more cell work there. The material that goes to DWPF is the more higher reactive material. So all our samples are initially manipulated or worked on in the cells. So here's a visual of inside the cell. On the left hand, you can see that. You have the manipulators. For visual, you see that filter 250 that actually Steve mentioned today. That's about 4 feet tall, so it kind of gives you a good perception of the height. Those arms extend up to 5 feet, okay? On the back side, you'll see samplers, and that's how we sample, and I'll go a little bit over that in the next few slides. But if you look at the, let me see if I get the pointer. If you look at here, I don't know if you can see it, but it's like kind of like 2 fingers, and they open and close. So here you see kind of like a grip. Our workers, our techs, they put their hand in that grip, and that's how they open and close those fingers. So imagine, when you pour something, let's say some water into a cup, that may take you like less than 1 minute. But when you're doing it with these manipulators, you're now having to use it with mechanical arms. It may take you now 30 minutes to make sure that you do it accurately, right? With science, everything has to be accurate. So it takes a lot more time to be able to perform work with it than it is to do it hands-on, but it protects us, right? These cells, that concrete is about 24 inches of concrete, about 2 inches of concrete that helps protect us, that shields us from that radioactivity. We do a lot of sampling, we do a lot of processing of samples in the cells before they come out to the lab. And what we do there's some analysis that cannot come out of the cells, and we have to do them all in the cells. And then some of the manipulation is making it less concentrated. Let's bring that dose down so that we can bring it to a level where the workers can actually work on it. Once they come out from the cells, it goes to a glove box. Like I said, by the time it comes to the glove box, we've done dilutions, which is kind of lower the concentration. We've done aliquoting, which means just taking a small portion. Instead of bringing out 40 milliliters, we bring out maybe 2 milliliters of volume, and all that reduces the dose rate. There is a limit of what can come out of the cells, and then once it comes out to the cells, it goes into glove boxes. Glove boxes also provides shielding. And it also has, and when I say glove boxes, it's because these here are actually gloves. They're neoprene gloves, and our workers put their hands in there, and that's how they kind of have hands on samples. And there we do further work on them. We do further dilutions. And when I say dilutions, it's kind of like, if you have, I don't know, I like coffee, so I'll use that as my example. But if you have really strong coffee, which I like really strong coffee, but if you're not comfortable with really strong coffee, it's too bitter, then what do? You add some more creamer, right? And then you taste it, it needs some more, and you need some more. And that taste of coffee and that acidity goes down and down and down. That's dilution. That's you're diluting that taste, you're diluting that acidity, and that's what we do, but we do that for radioactivity levels, right? We add some additional chemicals to be able to reduce those rates before they can come out for hands-on work. So sampling capabilities, so how do we sample? So the tanks that we sample in the different facilities, they're piped in directly into the lab. If you remember that picture on the left side of the cells, back there said there's samplers there. This is what the samplers up close look like. You see this right here? So if you look, this is the sampler itself. This is a vial within the sampler. So we have about 18 samplers at SWPF in the cells and about 10 of them at DWPF. They're tied in, if you see the piping, directly into the tanks within the facility. When operations is ready to sample, they notify the lab. Because the operations have different things they need to do before we can sample, like agitate it or bring the temperature down. So they notify us, tell us they're ready, and then we pull a sample. And when I say we pull a sample, it's not just one. Like for example, before we transfer decontaminated salt solution to saltstone, we have to pull a sample and give them a report. We actually pull about 25 vials because there's all these different constituents that we have to analyze for. But it all goes into one report, which we call it one sample. So in the cells, that's where we go and sample the higher radioactive samples. And then we do have some in the glove box as well at SWPF, because we have streams that are low activity, such as the decontaminated salt solution that goes to saltstone. For the glove boxes, you can see the technician uses the gloves to be able to pull the sample. In the cells, we use those manipulators, those robotic arms. We use that to put the vial in the holder, and then as a finished sample, we take the vial out. We have to recap them, and we do all that with the manipulators remotely. And then we have radio hood and radio benches. So once we do our work in the cells, and then we transfer them to the glove boxes, and we do even more work to bring the levels, activity levels, really low, then it can go into a radio hood and radio bench, right? The radio hood and radio bench, this is at ETF, has radio hoods. Everything at ETF is low level, so they do not have hot cells or glove boxes. And this one is in the lab at DWPF. Both SWPF and DWPF also has radio hoods and radio benches. And these radio hood and radio benches have a ventilation that has an airflow that go away from the technician. If you see the glass sashes that it has, it goes away from the technician. These hoods are checked yearly for airflow, making sure that it has the proper airflow. They have a streamer. You can see actually the streamer in this picture right here. See how it's going away from the worker? That means there's good flow going away from the worker. And they also have an audible alarm. So if there's a meter on there, if the flow goes below a certain level, it will alarm and tell the technician to get out. So our instrumentation are in all those areas. We have instrumentation in the cells for analysis that require a sample that's not diluted at all, and you have to perform the samples without additional prep. We have instrumentation in the glove boxes, and we also have instrumentation in the radio hoods. So what the lab technicians do is do all that preparation work before he can get on the instrument. It's kind of like when I say preparation work, it's kind of like a recipe. And for anything, I don't know, for those who cook or especially bake, you have to be very precise when you cook. There's a specific recipe to be able to get everything together and put it in the oven. Well, preparation is all those different steps you have to take before you can put it in the oven to cook, right, and to have a final product. That's what the lab technicians do. They do all the preparation, and then they get it on the instrumentation to get our final report. So for continuous improvement, just like the facilities, we strive to always continuously improve and find efficiencies within our processes. One of them, expanded analytical capabilities. I did mention that we do send quite a bit of samples to the Savannah River National Lab. When we were doing studies for the solids at SWPF, we send a lot of samples to SRNL for specific analysis. And then, we just thought, hey, there's some of those. We actually have room to be able, and the knowledge, the scientific knowledge to be able to do some of those analysis. So we went and bought some additional instrumentation that will allow us to expand our capabilities and internalize some of those analysis. What does that bring us? First, it will reduce our turnaround time. Savannah River National Lab supports many clients within SRS and other facilities in the DOE complex. So there is, a longer turnaround time based on their priorities. So this allows us to reduce that and kind of be the owner of what the pros' priorities are. And obviously, us doing it in-house, there's a lower cost to that as well. With the manipulators, obviously the manipulators are very key to our process. We do a lot of work in the cells, and without the manipulators, we cannot do that work. So it is key for the lab to always have good manipulators and have spare manipulators and then working adequately. But now there's with the manipulators, a lot of work that we do, a lot of repetitive movement, and of course, like any instrumentation, it can break, right? So SRMC has put together a maintenance team dedicated to repair and do preventive maintenance on the manipulators to extend the life of them. They centralize a repair shop at DWPF. They identified and tested, we also identified and tested parts to extend the life of manipulators. Our manipulators, they're made with aluminum. We did find out there's some manipulators are made of stainless steel. So we're looking into possibly substitute some of our manipulators for more sturdier, stronger materials. And then the manipulators are also, they use like these cables for the movements, and we're looking into maybe some stronger materials to hopefully extend the life of the manipulators. Now, when a manipulator breaks, then we have the maintenance team that comes and pulls it, does their repairs, and then puts another one in. So we have quite a few spares to be able to get back online in a timely manner. We talk about reliability, as I mentioned. The facilities, we're a supporting organization. The facilities depend on us to provide them that report. If they don't have, for some of the, especially for transfers to other facilities, they can't transfer without the report. So we need to ensure that we do not stop the process, but by not being able to support. So a few things that we have in place to ensure the reliability is equipment redundancy. All our analytical equipment has more than one, right? We have more than one, so if one breaks and is out of service, we can go and use the other one while we try to troubleshoot it, try to repair it, and sometimes we have to bring the vendor out to come and help us repair it as well. Upgrade of instruments, technology. You know how technology is. You buy a phone this year and next year it's obsolete. Very similar to analytical equipment, just a little bit longer in time. But we do a lot of research, communicate with the vendors on when is this equipment when is a new model coming out? Because usually when analytical equipment, a new model comes out, that means that soon enough, that company is gonna stop supporting their older models. And they'll start developing parts for them, and then we won't be able to fix them because we can't get parts. So we keep, we upgrade instruments when they start becoming obsolete or getting close to that, and making sure that we keep up with that technology as well. And then spare parts inventory. Of course, for us to ensure that if anything breaks and lab-wise when it comes to equipment, keeping a robust spare parts inventory is key to ensure that we can get back and running quickly in a timely manner. So I think all our speakers talked about, Steve and Doug talked about all the initiatives for the Climb to 9. And I have, if you see, there's little stars in a few of them. And that really indicates which of those initiatives that lab contributed as part of that optimization scope. We provided support, maybe sampling and providing data to ensure that that new improvement did make a change. Sometimes some of the initiatives we just sampled to be able to send out to SRNL for additional analysis. For like a 250 filter, we cleaned the cells. Our lab technicians are experts and manipulators, and we supported that evolution by helping the deconning of the cells so we can get someone in to be able to do that work. So the lab, we support our day-to-day process, but we've also did a lot of support to achieve, for the facilities to achieve their Climb to 9 initiatives and to be able to meet our goal of 9 million gallons per year through the different facilities. So in summary, SRMC Laboratories' mission to safely provide analytical support to the facilities. As I mentioned, we're key. We provide the constituents of the different tanks to be able to make sure that the process is working well, provide information in case we need some troubleshooting or something's not going as expected, and information that is needed to be able to transfer the materials to the downstream facilities. We support the day-to-day analysis in addition to planning and support the Climb to 9 initiatives. And we do continuous improvements of our processes. We try to find efficiencies in our process. How can we do that analysis quicker? What can we do to ensure that we're being safe? We try to make, it says here, we ensure that we meet our turnaround times. A lot of our samples are time sensitive. For example, for the decontaminated salt solution to be able to transfer, we get a sample and we have to turn the results around within 24 hours. So we try to find efficiencies to be able to reduce how long it takes us to provide that report and overall be able to support the SRMC throughput goal of 9 million gallons of salt waste processed per year, because overall our mission is to be able to maximize our operations, to be able to more efficiently and quicker process that waste to be able to close tanks. I think that's it. Yep. That's all I
Okay.
have.
We'll start with Sade.
My name is Sade Shofadia, SRS CAB. Thank you for your presentation. I have a few questions. I'm curious about the construction of the glove box and the I know it's supposed to be a very protective barrier. I don't know what that material it is. It looked like, I don't know what it looks like, but it looks like thin material.
It's not really thin.
Okay.
Actually, it's about 24 millimeters of thickness. It's made from neoprene, a very resistant and sturdy material. And the thickness is based on what work that we do, and also is based on dexterity as well. There are some that are a little bit thicker, like at DWPF, we use it mainly to be able to bring samples in and out. But at SWPF, by the time we bring them out from the cells, they're very lower radioactivity levels, so that provides enough of thickness to help that protection, but also gives us dexterity. There's still a lot of work that we need to do with the glove box's gloves to be able to perform the work. I mean, we use little vials, they're literally this small, that we have to be able to hold. So a lot of that, and all that has been evaluated through engineering. These are the common thickness that are used throughout different facilities in DOE complex. And they're very sturdy and provide the protection that we need, not only just radiological, but also chemical.
Thank you. I'm also curious, will you please describe some of the sampling methods and analyses for SWPF and DWPF?
So all our sampling is done within the cells or the glove boxes. I showed you the pictures of the samplers. So what we do is when operations is ready to sample a tank, they let us know that, hey, we're ready, can you prepare, can you start sampling? We use the samplers themselves to be able to get the liquid out of the tank, right? Depending on what tank it is how much volume that we get. For SWPF, each vial is about 40 milliliters of sample. For DWPF, we use smaller vials, or about 12 mil vials. And depending the tank, is what the type of analysis that we do. For example, for the decontamination salt solution that we sent to Saltstone, I mean, we do nitrates, nitrites, we do sodium, we could do gross alpha, gross beta, gross gamma, cesium-137, strontium-90. It's a huge suite of analysis, and those analytes have been set by engineering, right? This is what we need to know to make sure that your stream meets our requirements so that we can use it for further processing. So each tank will have a different analytical requirement. Did that answer your question?
Yes, thank you. I'm also curious about your new analytical tools or new instruments for analysis.
So we went and bought a few, and to me, there's like a new toy, so it always makes me very excited. And I am a chemist as well, so obviously my nerdiness comes out when I talk about instrumentation. But we did go by, so one of the analysis that we had Savannah River National Lab do for us, especially for solids, is X-ray diffraction. And what that does is take solids and really look at the overall structure of the solids. And I'm like, well, we have a chemist who did their PhD thesis on it, so we can do that ourselves, and we actually had a space for it. So we bought it, we're working on getting it installed and developing our methods, and now if we have any more additional studies that we need to do for solids, we can do that in-house. We also bought a new mercury analyzer. So SRNL has a mercury analyzer where you can just take the sample, not do a whole lot of preparations, and put it on the instrument and get a number. And you can use it for aqueous samples, for organic samples, very easy instrumentation. I'm like, well, we have a chemist that specialized in this instrument before, so we have space for it, let's go buy it. So we went and bought one, and we do a mercury analysis on the salt batch feed that we qualify before it comes to SWPF, but that will also allow us to do any mercury analysis for the facilities. Even though that instrument will be at SWPF, we'll be able to use it for samples if DWPF needs us to do any, or any of the other facilities. Tank Farm will be able to support some additional analysis on that. And then we also went and bought, what did we, a deposition setup. So, and that's for plutonium and uranium analysis. Our previous technique, you had to concentrate the sample, and while it does provide a good technique, and that's what a lot of the facilities do, it takes a long time. So we bought this deposition setup, and this is what companies that do standards, there are certified standards that they sell to different organizations. They use this technique to prepare their samples, and it provides a more accurate analysis, but also a quicker preparation, and it removes some of the hazards that actually concentration process had. So, and I think and we're in the works of probably thinking about a few more things, but Steve, I haven't pitched it to Steve yet, so I'm gonna keep them to myself for right now.
I'm curious about what is the average time for analysis? I know there are a variety of analyses that you go for.
So it really ranges depending on the instrumentation and the sample preparation. So like, for example, when we want to do pH, how acidic something is, that only takes, well, in the cells, it takes about 4 hours. But in the glove box, it probably takes 2 hours. But now we have another one that, Steve had mentioned that through their process uses the CSX solvent. That's one of the constituents of that solvent is isopar L, and all the facilities, Saltstone and DWPF, have a very hard limit of how much of that can be in the streams that we send to them. So we do that analysis, and that analysis actually takes about 12 hours, and that's between preparation time and instrument run time. So it does vary highly. And then one of our analyses is density, and that's just taking a measurement and weighing, and even in the cells test takes less than an hour. So it just really depends on the analysis. So we have those hard turnaround times. We have turnaround times, that means you need to get this number or this report out before it stops the process. And all that is based on the movement of the process, but how long that takes for us to be able to get it out as well. And we report everything at one time. So if for the decontamination salt solution, if there's 15 analytes, we report once we have all of them completed on one final report.
Oh, I'm also curious about, you guys are doing a great job at SRNL, and it's one of the top labs in the country.
Are we doing what again?
So you guys are doing a great job at SRNL. I believe it is one of the top labs in the country. I'm curious about if there are any challenges at the lab.
So I will say, and I think this is a challenge that everyone is facing, a lot of our most experienced people are retiring, right? And so now we have a lot of a very new workforce. We have people who are just now starting to work, starting in their career, learning the processes, and we're losing a lot of that experience. So just working on training people and trying to get our staffing in the level that we are, but now we're about to lose. So making sure that we highly document what we've been doing, being able to train people before they leave. Like, I'm gonna have a first line that's retiring next year, and I'm ready bringing on board the next person so they can learn before they leave and kind of get a lot of that knowledge from that experienced person. And then for some of it is also the aging of equipment. DWPF has been operating for many, many years. So a lot of we have a lot of aging of equipment and obsolescence of equipment. But we stay on that we do evaluations, see what can we do, what is the next thing we need to work on before it becomes obsolete, what is the next equipment we gotta buy before the vendor doesn't support it anymore, and what can we do to upgrade. And even for SWPF, we just recently came online, but we bought those instrumentation and did a lot of method development before we got online. And even now, I think one of the instruments that's only about 8 years old or less is the vendor said, oh, we're not making that one anymore. You're gonna have to go to our new model. And that's one of the things I'm gonna have to go buy. And I have 2 of them at SWPF, I have 3 of them at DWPF, and now we're gonna have to go to the newer model because they're gonna stop supporting it, which means they're not gonna make parts for it, so we won't be able to repair it. So a lot of it is the new workforce and trying to get them trained and get that, try to keep that level of expertise that we have, and then also the age and obsolescence of equipment, I think, are our biggest challenges.
I have 2 more questions. So this is outside of DWPF, and you guys know what I'm talking about. And but I'm curious if you guys have conducted any longitudinal studies on the health outcomes for your lab techs, as far as any longitudinal studies on health outcomes for your workers in your lab that have interacted with?
So all our workers in the lab and even just that go through the radiological buffer areas, they wear dosimetry. And that dosimetry goes, every quarterly is sent in and it's read to see how much they've been exposed to, right? And then the lab technicians and even chemists that work hands-on in the radiant hood, in the glove boxes, they're called finger rings. They literally look like rings that they wear on their fingers. And that monthly is also sent off for readings and see what has been their exposure. And that is kept tracked and reported. And the workers themselves get a report yearly on this is what you've been exposed to. I think it's quarterly. This is what you've been exposed to based on the dosimetry readings. Was that answer your question?
Yes, that's very cool. Okay, my last question. And perhaps it might be a new instrument for you guys. And those who don't know me, I absolutely love honeybees. Honeybees are reliable, through empirical research, has supported that honeybees are reliable eco-indicators and just living samplers. And in fact, the Department of Energy Office of Science, they've even trained honeybees to detect bombs and radioactive materials. I read an article last year about some of the groundwater contamination along the site, and we're always exploring the health impacts in the areas around the Savannah River site. Is there an interest in utilizing honeybees to explore, potential contaminants for areas where you guys aren't sampling? Or just you can literally assess and examine any byproduct from the honeybee, whether it's they're just taking them apart or their honey, the beeswax, their pollen, their royal jelly, you're able to detect lead, toxins, any other chemicals. So it might be a good tool for sampling the impact of the site.
Well, it's very interesting. I've actually never heard that myself, so that's probably a really good study to go look into. I think that would be something that, environmental health and safety would be the right person to really evaluate if that's a feasible means to go and for our facility and for SRS as a whole to see if that is something that they can utilize for health studies. A little bit outside of the lab scope, but really interesting, and we can kind of give that information to environmental health and safety and just kind of pass on that information. So I appreciate that input.
Thank you.
Okay. John?
John Thomas, CAB. Thank you for the presentation. The question I have is around what happens if the quality that you're testing doesn't meet your standards? So you said within the process, like the finished glass product. Now what happens? What's next steps?
So the lab is in the business of data and numbers. We provide numbers to engineering and to operations, and then engineering goes and evaluates that data. They do additional calculations, they do additional analysis and trending analysis, and they're the ones who decide this does not meet our quality or this does not meet our spec, and then they're the ones who take that data and decide what is the next step. Kind of out of the scope of the lab other than providing the data, but it is engineering and of course, management with their advice of engineering take action of what the next step may be.
Okay. Yeah, it's interesting because we never asked that question. What happens if it fails or you get feedback that it isn't acceptable? So, Okay. The other thing I had was, what do you do with all the samples?
So our samples, they go right back, whatever that we do not utilize, since they have been sampled within the facilities, that means they're compatible with our processes. Whatever we don't use, we put it right back into the process, and it continues through the process.
So what happens to what you do use?
So what we do use, a lot of it does go back into the process as well if it's compatible, and what's not compatible, then it is managed as any other through the management waste disposal regulatory processes.
So it could be radioactive?
Yes. Mm-hmm. And we work through our environmental and waste department for the path forward on disposition, which is any disposition of per the regulatory requirements to be able to dispose of that.
Okay, thank you.
Okay. Pat?
Pat Kilroy, CAB. I was wondering as I was listening to you, I know y'all have a set of standards for everything. Mm-hmm. Well, over the past 20 years, how much has these standards changed?
When you say standards as in chemical standards?
I'm
or do
talking
you
about
mean...
release of water, stuff that, that goes out, stuff that, say y'all process water and it's ready to go back to the streams, the ground, everything else. Has the standards changed over the years?
So when you say standards, like what are the requirements for it to be released? The lab, once again, lab does not really do those evaluations. We provide the numbers or the data for engineering to be able to process and make those evaluations and do all that trend analysis. So any changes of what those limits are or that needs to be met to be able to do the release, that would be more in the engineering line of scope, not the lab scope.
So you're saying engineering determines what is acceptable and what is not?
Well, engineering evaluates the data that we provide them if it's acceptable or not, based on some standards or limits that have already been implemented.
Just to clarify, so for water releases and things like that you're asking about, there would be permitting standards and everything that applies to that. I can't answer the question whether or not there's changes, but that's a question that we can take back and get answered. Just so that we're clear what Melissa's here for. She's here for the SRMC, the Liquid Waste Contractors Labs. So the liquid waste programs, laboratories, and assessing those waste streams specifically is what she's here for today. Not to cut off questions, I apologize.
Thank you. Thank you.
Okay, that's all.
Amy.
Okay.
I don't want to go in front of any of the CAB members, but if there are no other questions, Melissa, I'm curious, on your slide 4, you talked about your lab technicians and the new hires that you bring in and how you train those folks. If you're training them to the degree that you are, what sort of training do they need? I mean, what college degrees are you looking for is what I'm asking. Can a person come in with just a high school education, or is somebody
so for
who's looking for a
laboratory
job?
technicians, there's no educational requirement other than a high school education. We train them, when they come in, they sit in a classroom for months, and we train them for all the basics when it comes to safety. We give them chemistry, we give them math, we give them safety, they learn about all the facilities, liquid waste as a whole. Other than, they do take an aptitude test. They do go, Aiken Tech provides this aptitude test. I think it's like locating information. There's 3 different aptitude tests that they have to take. Comprehension, and I can't remember the other one right now.
Is that like the work keys?
Work keys,
test?
that's right.
Okay.
They do take work keys. There's 3 areas they have to take, and they have to get a specific score, above a specific score, to be able to apply. But other than that, in high school education, there's no requirements. Now, our scientists, our chemists, do have to have a science degree. In chemistry and biology, we've had geologists, but for our more scientific workforce, they do have to have a science degree. We have lab technicians that this was their first professional job, and they're just going into the workforce. We have those that worked in the medical field or work in other chemical industries or Bridgestone, different industries around the community that come and work for us. But we train every skill that they need, every knowledge that they need to be able to be successful. We provide them that training.
Any other questions or comments from around the table?
I also take compliments.
Compliments from around the table as well?
Thank you.
Thank you. All right, y'all ready to go into the next one? All right. So let's see the end state for some of this waste. This will be the SDU construction update, a little bit of operations. And I've run out of words, but they're almost up here anyway. So folks, whenever y'all are ready. Thank
I'll give you my mic.
Hey, good afternoon. My name is Brandon Witt. I'm the Director over Projects and Construction Services for Savannah River Mission Completion, and I'm co-presenting today on the mega construction update with
I am the Deputy Federal Project Director for the SDUs. And I'll let him go first.
Yes. So everybody's seen this slide through numerous presentations today. So I'm here to talk about what's in the red. So what is a salt stone disposal unit? So as you saw in the video this morning, the SDUs are the final stage for the decontaminated salt solution, or the DSS, after it's been mixed with the fly ash and the slag at the salt stone facility. So our job is to construct these final resting spots for that waste. You know, as we went through it and as the video talked about this morning, the SDUs are permitted as the landfill with the state of South Carolina. So again, these are the final resting spot for the low-level waste for the liquid waste program. So how do we get to the mega SDUs and why did we change? So in 2013, we had constructed 6 smaller tanks here at about 3 million gallons capacity each. So as if you look and you expand that across the entire liquid waste program to get to 2037, we were going to need 82 of those tanks to complete the mission. So you look at the real estate that was going to be needed to complete that. So at the time, they developed a team, they realized they needed to scale this up. So how are they going to scale this up and still meet the requirements that we had on site? Because they had already been very successful with the smaller units. So they put together a team and they went out and looked at multiple designs, multiple different ways to do this. And so they came up with a, I'll say, modified commercial water tank design associated with this. Water tanks all across the country are being built using this same design, and they can be up to tens of millions of gallons. I've seen some up to 40 million gallons using this design. So when they went around, they looked at it, they said, yes, they can modify these water tanks for a nuclear environment. They're not much different than the ones we're already using. We can scale them up. And so we did. And so by doing that, we came up with the mega SDUs. And so as you can see here, they take up less footprint, use economy of scale, 33 million gallon capacity tanks, 375 feet in diameter, 42 feet tall. By doing this, we only need 7 tanks to complete the liquid waste mission, SDUs 6 through 12. We've done numerous estimates. We've looked at number of studies associated with it. With the cost savings, by going the mega unit versus the smaller ones, we've estimated somewhere around a $500 million cost savings associated with it. So how did we get to that? So economies of scale, right? So you get more bang for the buck the bigger it is, more gallons in a smaller footprint. So we were, at the time, it was costing somewhere between $12 to $15 million to build these smaller ones. And I'll tee up Chrissy a little bit, and she can give you what the cost is today as we get to it. I don't want to steal her thunder on the last slide there. So, but just know it's a lot cheaper than what we were doing at the time. Multiple stages to go through to get to actually build the tank or to build an STU. So we go through site prep, mud mat, and I'll go through each of these in a little more detail in the following slides. But as we go through each of these phases, you see it takes 4 to 5 years to actually construct the SDU, the mega SDU. So when it's finished, this is what it looks like. So how do you compare that? How do you get a gauge for what that is? So Madison Square Garden in New York City is comparable. It's about actually 15 foot larger on either side. So it's got about a 30 foot larger diameter than what we're actually using there today. So if you've ever been to New York City, you've seen Madison Square Garden. That is somewhat comparable in diameter. It's much taller. It holds like 25,000 people. We can't put that many people in there. But just to give you something for scale associated with it. Moving on to the stages. So the first stage is the site prep work. You dig a big hole out there. You go through there. You make sure the site's cleared. We excavate it down to the required depth. We move utilities as needed through there. We install new utilities. The site prep is critical because that is the foundation for everything else on top. So we have to make sure we get that correct. We do a proof roll of the site after that's finished. We bring geotechnical engineers out to check that before we move on to the next stage. So we make sure we spend a lot of time and effort to make sure we get that part correct. Moving on to the next phase, we call it the mud mats, which is just unreinforced concrete. We put those down for multiple reasons. One, it protects the ground. So we spend a lot of time and effort getting there, geotechnical guys coming in. We want to protect that. So we put down a concrete mat to work on that. It's also a cleaner workspace as we move up the tank associated with it. So if we just left that as bare dirt, weather comes in. I'll show you a video in a minute. We get lots of weather. Weather comes in, gets a lot of mud on it, a lot of worker safety associated with that. So you put down a clean working surface to work from there. So we have a 2 mud mat system associated with it. So the first mud mat protects the ground underneath. The upper mud mat protects going forward. But between those 2 mud mats, I took a cue from Steve this morning, have some show and tell. We put a HDPE liner in between there. So this liner is part of the leak detection system associated with the SDUs, and I'll pass this around. And so this is installed between the lower mud mat and the upper mud mat, and when the tank is constructed, it is tied back in, and like I said, it's part of our leak detection system. So you can see it's a pretty hard material. It's pretty durable. It does allow for the concrete to be poured on top of it and not damage it. Next, cell construction. As we move through, as that's going around, I still have more show and tell that comes with this also. This is the floors, the walls, the columns, the roof associated with it. About 17,000 cubic yards of concrete associated with it. We do that in sections. We got 14 floor sections, 25 wall sections, 208 columns associated with it. The good thing with cell construction is we hired the company that goes around the world building these tanks for water tanks. We hired them to build those for us here. And they've built every one 6, 7, 8, 9, almost finished with 10. They have the contract for 11 and 12 also. So that company, this is all they do is build these tanks, and they've done fantastic building them for us. After the walls get finished, the roof gets on. We call it a hydroblasting, basically a pressure wash around the exterior of the tank to get the profile we're looking for. And then show and tell number 2, so pre-stressing cable. So this cable gets put around the exterior of the tank. There's 341 miles of this cable that gets wrapped around the tank. 341 miles, so I'll pass this around. So why is that? So if you put 33 million gallons of water inside a tank, you expect it to expand and contract, right? By putting this on here, it minimizes the expansion associated with it and protects the integrity of the tank. So really good design, very well thought out, and it takes, I don't know, months to go through that process. And so it is a multi-stage process of putting the pre-stressed cable on. So after we hydroblast, we'll put a layer of shotcrete on, wrap from bottom to top the cable, come back, put shotcrete in between it to protect the cable, and then do the same thing. We do it about 6 times, going all the way around that tank, again, to get to 341 miles, about 82 reels of cable associated with it. Every step of the way, every time we do concrete, shotcrete, whatever it is, we apply a water cure to that. So we continuously keep it wet. It just minimizes cracking as we go through there. There used to be chemicals you could use to put on there, but now we keep water on there to make sure it's a tried and true method associated with it. So water curing is the way we go through with that. So I have a time-lapse video here, maybe if I can get it to play. I just wanted to show part of what they go through. So I want you to pay attention to the equipment they use, the concrete trucks they come in. This is taken over about a 6-week period. But I also want you to just pay attention to the weather, and I'm sorry, the weather that they go through. We get lots of rain out here in May, June, and July, and we still are able to make great progress associated with it. So this video was taken over a period of probably about 6 weeks. During that time, we were able to pour 7 of the wall sections and about 50 columns during that time. So even with the weather you see there, the delays, the way they have the forms already prefabricated for the columns and the walls, we're able to account for that, able to move quickly when the weather allows it. We're able to perform very well when it comes to concrete placement work. So again, that was just a quick snapshot video of the progress we make out there. Again, we've done multiples of these, and this was just one example of how we use it. Next slide. Okay, so I'll start at the top and I'll work my way down. So once the tank is completed and we get the roof finished, we start with balance of plant type work on top of the tank. So we do all the piping, the supports, the electrical, the instrumentation. There's some miscellaneous work off the tank with some equipment skids, piping coming from Rodney's facility over to the tank we install. All that is being done on top of the tank once it's finished. At the same time, on the inside of the tank, we're installing a rubber liner through there. And I'll hand out a different type of liner, which is different than what was between the two mud mats. So this is a bromobutyl liner system. Basically, it's a rubber liner. Why rubber liner inside the system? Because when you put that much waste inside the tank, it does expand and contract. So you do need something to be able to expand and contract with it. So a rubber liner was chosen to go through that. It's worked very well. There's about 7,500 pieces of rubber that gets laid on the floor and the walls. That takes approximately 6 months to do that from top to bottom. Very well thought out process. SDU 6, with the rubber that was chosen, the amount of testing that we did, there was only one source in the world we could get it from, and that was in Germany. Between when we finished SDU 6 and SDU 7, we found actually a domestic source who could make that for us. And so now all the rubber we get is made here in the U.S. And so it was a great product that they were able to develop for us. We were able to domestically source it, and we didn't have to ship it from overseas. So that was a good news story associated with that. Once the rubber's installed, how do you know the tank's good, right? How do we know it's going to hold what we want it to do? We actually turn around and we put 33 million gallons of water inside the tank just to make sure it doesn't leak. So we have 3 wells drilled around the site. We pump well water into the tank. We start filling it up. It takes about 24 days to fill. Again, how do you know if it leaks or not? Well, it could rain. You see water around the exterior during the rain. We add an environmentally friendly dye to the water to detect it. And then we do the test at night with a black light to see if there's any leaks associated with it. So once we do that and it fills all the way to the top, we hold it. If we go through do the black light test, there's no leaks, then we start the draining process. It takes 18 days to drain the 33 million gallons of water out of the tank. Where do we drain it to? It's well water with an environmentally friendly dye. We drain it back to the ground, goes to our holding ponds, and eventually to the creek and back to the water supply. So, and then after that test, there's some other minor testing we have to do to make sure the facility, the electrical components, the piping components, everything else is associated with it. So we do complete some testing before we turn it over to Rodney for him to operate. So with that, I'm going to turn it over to Chrissy, and she can take you where we are today with the construction and through all the rest of the SDUs.
Yeah, so I actually still measure my time on this project in months, so they chose to give me the easier part of the slides. So we're going to talk about the current status. I actually passed a year in May, so I've been around a little bit, enough to know that 9 was really cool when I got to walk through the inside of 9 after they put the liner. So I've seen most of it. So what you're looking at here, red button, there we go. Okay, so what you're looking at here is 6, 7, and 8 are on either side, 9 is back here, and 10 is back here. So SDU 6 was completed. Initially, that was our first one. It's now operationally 50% filled. 7 right next to it here is now about 16% filled. Not currently being filled. 6 is the one that's currently being filled. 7 will follow, 8 will follow that, and 9 will follow that. 8 and 9 were actually completed over the last couple of years. 9 was completed in April. March, April timeframe, and then 9 was completed in March, April timeframe. 8 was completed last year. And so now we're basically just looking at the last 3 construction projects. So we've got 10 back here in the back, and it's pretty much built. So we've got a big monolithic concrete structure out there that looks like a tank. So we've got some final, like he was talking about, the liner will go in shortly, and I'll talk about the rest of the construction on SDU-10 in just a minute. 11 and 12 are going to be in this nice section right here that's already prepped for them. We plan to start 11's mud mat here in the next few months and 12 by the end of the year. So the smaller units that he talked about are here and here. Those were completed long before these started, and all of those are filled and completed. Nothing else to be done with those at this point. Not filled, not completed in construction a long time ago. And there we go. So here's 10, and here's that really nifty piece of equipment that DN Tanks uses to wrap the cabling around the tank. So at this point in time, we've completed all of the wall sections, all the floor sections, all the columns, and all the roof. So this is what we're doing right now, is watching this machine wrap around that tank over and over and over again. They've done hydroblasting. They've got several layers of shotcrete. They're working on the 341 miles of pre-stressed cable. Now, he mentioned that several times. Now I'm mentioning it again, and I'll just give you a little perspective. 341 miles is the distance between here and Disney World. If you're boring like me and you've never been to Disney World, it's also the distance back and forth to Atlanta. So if that gives you any idea. So the next time you get to go to Disney World, think about that. Like I mentioned before, the next step after we finish with the cabling is going to be the liner installation inside of SDU-10. So that should start in the next few months, probably early next year. And this is the site, like I said before, for 11 and 12. By the end of this year, you'll see a lot more work going on this section. The mud mat should be installed here soon for one of them, and then the floor sections will start thereafter. So like I said, that was the easiest part. And now the fun part I like to talk about, although the SRMC has done a great job because I can't really take too much credit for this. But this is kind of an outline. It might be a little bit of an eye test, but this is an outline of what the cost has looked like over time and what we've done to improve and streamline the projects. So since SDU-6, we started with SDU-6 and 7 as singular projects, singular builds. So SDU-6, with 2024 dollars, we spent $152 million. Same thing in SDU-7, $143 million. We saved money and time. Then we got smarter, and we said, let's try to put them together and make a project out of multiple units instead of just one at a time. When we did 8 and 9, we saw it go down to $109 million per unit. And then in 10 and 12, it's still to be determined, but we fully expect that'll also be on track to be less than $109 million per unit at this point. So we expect all of the SDUs to be complete by July of 2030. That's our milestone deadline. Based on our history, I expect it to be done much sooner than that. As you can see on the end, I'll just give a little bit more, some more kudos here. In 2017, SDU-6 won the Project of the Year, and in 2018, it won Project Management Excellence Award. And in 2021, SDU-7 won also the Project Management Excellence Award. So the projects have a history of incredible success at the site. And I believe that's it. So I guess we're ready for questions.
I think it's just a summary slide, isn't it?
Yeah.
Oh, there's a hole there.
Is there one?
It's just.
Oh, there it went. Sorry,
just
I was
a
hitting the
question.
button.
That's fine. Okay. Pat, we'll start with you.
Pat Kilroy, Cab. What is the composition of the cable you're putting around it?
And that's the technical question. I'll pass to him.
Actually, I don't know. off the top of my head. Tim, one of our experts is in the back. Do you know off the top of your head the comp? Yeah.
Okay.
Can we repeat that on a microphone for me? Because I didn't hear.
Is it galvanized? Is the cable galvanized?
Yes.
Okay. Let me ask you, y'all putting Shot Creek over this?
Yes.
Has any potassium dichromate been added to the Shot Creek?
Not to my knowledge.
And the reason I'm asking, because I live in Goose Creek in Charleston area. They had to redo the bridges because they had pre-stressed cables, and they rusted away.
Okay.
And the only chemical they found that they could add to concrete to reduce that, potassium dichromate. And what is the life expectancy of these cables?
So the tank itself is the secondary containment for the saltstone solution when it's mixed with slag and fly ash. So when it becomes a grout, that's the primary. So they take credit in performance analysis space after the site's finished, and we put an environmentally cap on it that within 1,500 years that the concrete would degrade and it would still be there. So that's the analysis they've done is 1,500 years.
Okay, thank you.
Yes.
Yeah, I apologize. Can you tell us the composition of the cable and the mic, just so we can record it?
Yes, it's a 6-stranded braided steel cable.
Thank you.
So.
All right. Phyllis?
Phyllis Britt Cab. I was wondering, what form does the material take that actually goes into these?
I assume you're talking about the grout that goes into the tanks?
Yeah, when you're filling it,
Yes.
after you're finished building it, what exactly is going in it?
So it's the material that Rodney discussed earlier that he talked about where the liquid feed comes in and mixes with the slag and the fly ash and the saltstone facility. That makes up the grout, and it's a consistency. It's almost like a water-like consistency as it goes through there. And it comes out and it's pumped from saltstone over to our SDUs, and it is dumped inside the tank at that time. Since it's the consistency of water, it basically self-levels itself, but even if it doesn't, we have multiple ports around the exterior of the tank that we can fill the gaps around if it starts pooling within a location. And Rodney stepped up to maybe help me here as a phone a friend.
Yes, I'm Rodney Blackman, Facility Manager for ESD. So basically, it's like any a grout-like material. So it's liquid as you pump it, and then it sets up, gels, and then it hardens. And that's so inside is you've got a hard material.
Okay, so when you start doing that, it's already sealed on the top?
Yes, ma'am.
Okay,
Yes.
so you're just
Yes.
filling it
That's right.
wherever.
Filling the interior.
Yes.
Gotcha, okay,
Yes.
thank you.
Okay. And Candace?
Candace Cave Cab. So when will we utilize SDU 9? Is that the newest one that we're talking about?
So that's again,
Yeah,
that's an
what's the
operational question.
Tanya?
So I'm glad Rodney's here to answer that. So it's under a management control plan.
Thanks,
Yeah.
Rodney.
Yeah, I don't have the specific date, but we're a couple of years out. So we've got to finish 6, we do 7, do them 8. And for the most part, they'll go in order. Once they're operational, that gives us some flexibility that, for instance, we already have some material in 7. Operationally, they were both available. We had a need to go from one to the other. So it gives us some flexibility as they come online. So as we fill and as that rate of throughput goes up, we'll fill them pretty much in order.
Thank you. Also, so if there's a several-year delay between the time you're finished with construction and you actually utilize it, do you do any additional testing, for example, with your water and how you fill it with the water? Do you do that again before you use it if you've been waiting
No.
several years?
No. Once we finish it and complete it and get it ready for operational use, that is complete. The next material that goes inside the tank will be the grout material that comes from Rodney's facility. It won't be retested again. Now, so let me say this. So inside the tank, they do have cameras inside there. So they do periodic inspections with the camera inside the tank to make sure nothing's degraded. They haven't seen any problems with it. So that is a secondary check that they have, including in the operational ones, so where they can see the fill height as it goes up. They do also have sensors in there with instrumentation that tells how high it is, but the cameras also are a help with that.
Awesome. Okay. So why are you releasing the water so quickly afterwards? Is it just to say you've done your testing part and now it's on to operations, or?
That is correct, yes.
Okay.
So we want to get the water out of there, get it ready, actually dry out the tank, because it depends operationally and when Rodney needs it. So when we finished SDU 6 and 7, it was a much closer need to getting it ready for operation. So it was a much quicker process to get the water out, to get the tank ready for operation. Now there is a little bit of time. Even though time is money, though, right? So the longer we wait, the more money we're spending. So if we go ahead and get the water out of the tank emptied, the tank turned over to Rodney for operational use, we can close out our project, save the money associated with that, and any other future costs come from the operation side, not from the project side.
Thank you.
Okay. Any other questions or comments from around the table? Concerns? Compliments?
We don't take compliments, sorry.
Thank y'all very much. Appreciate it. We'll just leave it there. Okay. No one has signed up for public comment, but I want to offer the opportunity anyway for anyone who may not have had a chance to sign up. Does anyone wish to make a public comment? Seeing none. The next step is board business, and this is where it's going to get a little bit awkward, because board members, I would like you all to raise your hands. Just do it for me. Just raise your hands. I promise it'll be okay. It's safe. Now count the number of people with raised hands. Is it less than 10? We ain't voting. There's not enough of you. Okay. So this recommendation will automatically be tabled until the next full board meeting. We will I know, it's heartbreaking for all of us here. There is a support group of people who have had this happen. I'll get you in touch, get you the emotional assistance that's needed. But we will add this to the agenda for the next full board meeting. Sadie, you have a question? Or Sade, sorry.
I was curious if there has been any updates on the recommendation as far as AI.
The AI draft is still being written. They're working on getting it finished and routed through.
Thank you.
Yep. Okay, so with that, we can't vote. Are there any other questions, comments, concerns that you need to have addressed, something you thought of over lunch that we didn't get to? I've noticed many of our presenters are still in the room today. So, yeah, Pat, let's do it.
Got one question.
Yep. Can you turn on your mic for me?
The grout today is slag and what was it?
Fly ash. That's what goes into the saltstone disposal units.
Yeah. There's no concrete in it.
They're saying
Zero. Okay, that's all.
Okay.
James, could you refresh our memory on how many board members there are right now currently?
There are 17 board members. And so you need 51%. That brings it to 9.5. And if you round up to a whole person, that's 10.
Thank you.
Phyllis and Candace. Phyllis.
Yeah. I just wanted to say, now having done this for 2 months, I like this. I felt like I really got it better yesterday and today.
Focusing on one subject area?
Yes.
Is it working better for everybody across the board? You like it better? Right? Okay. I'm glad that that's...
Thank you. All of them were excellent. And I think part of it is because we're more in tune.
Good. That was the intent. I'm glad that that worked. We'll see how it goes in September for nuclear materials. That is going to be a ride.
James,
okay. Yes, ma'am.
We're questioning your math.
Okay.
There's 17 members. 51%.
Divide 8, okay. You have to have more, it's 50 plus 1, 50% plus 1 board member, sorry.
Oh, we thought it was 51. I thought you
So,
said 50.
so if
Okay.
you take 17, divide it by 2, you get a number, you add 1 to that number, that becomes 9.5. Now you've got to round that up because a half a person doesn't exist.
Thank you for clarifying.
I'm sorry, I apologize. That is an important distinction. That is an important clarification, it is.
Thank you.
Are you sure about that? I thought it was 50 plus 1%.
It is 50% plus 1 person. So half of the board plus 1.
person.
Yeah.
That's not good.
Yeah, basically more than half of you have to be in the room. We don't round down, you got to round up. This is not 1853.
But that's still only 9.
I know. You want it, I know. I promise that
Isn't that still only 9?
It's not.
Half plus 1 more person is 8 plus 1.
8.5 plus 1 person because it's 17, not 16. So 17 divided by up, it becomes 10. I appreciate it. It is definitely worth double, triple, quadruple checking because it is a lot of time, energy, and effort to pull everyone together, and then you don't get to vote. I will tell you that the strongest thing that you folks can do is peer pressure. It doesn't matter how many times we say it, but if you start saying it, well, okay. And don't forget that there is an application in your folders. We do encourage you to hand that to somebody who is not just curious, but conscientious of calendars. If they could show up, I think that would be amazing. That would be a wonderful boon to our group. Also, one other note that we had, Edwin again did text in. He apologized again for having to leave early. His family matter has been resolved successfully, but we still keep them in our thoughts. Anything else we need to address before we hand it over to Phyllis? Take it away, Phyllis.
Okay. Just a reminder, committee meetings on the 20th, starting at 4 o'clock. The next full meeting is the 19th. Is that right?
16th and 17th, I believe.
15th and 17th. Okay. And it is where?
In Columbia, South Carolina.
Oh, that's right. Okay.
We get
So
to travel.
Pay attention to
We're
that.
taking it on the road.
Yeah. Okay. Thank you, everyone who is here. I appreciate it. As I said before, I think it's very successful. Without objection, meeting adjourned.
Thank you, everyone.